Hello, everyone. Welcome to the Salon. We are very excited. What's happening? Yeah. We're very excited to be here for the 18th Salon with Kim Stachenfeld, one of my absolute favorite humans on earth. And we are very excited to listen to her. A reminder for anyone who's joining us for the first time, the Learning Salon is a forum where we gather every Friday at 4 p.m. Eastern Time of the US. And we have interdisciplinary audiences and speakers. The speaker usually talks for about 10 to 15 minutes, and then the three of us ask some questions, and then the audience asks questions. You can post your question in the Ask a Question area and then vote on each other's questions. We usually invite people with the most voted question to come on screen. It takes about 2 hours. Sometimes we go over. If you need clarification, please ask in the chat area. Hi, Kanaka. Kanaka and Brad are going to be facilitating answering some questions in the chat if we are too busy talking and we don't see it. Feel free to ask a question if you're a junior person. If you're from a different discipline, we encourage that kind of interdisciplinary dialogue. We think that that's a neglected skill in academic world. To just discuss things with expertise, with due diligence, but just to discuss things with a lot of respect and in good spirits, and in a spirit of camaraderie. This session is particularly exciting for me, Kim, and I'm going to just briefly introduce her. I know Kim for 8 years now. I was thinking the other day, it's a long time. And she's one of the first people that I met when I moved to the US, and I immediately knew we were going to become friends. And she not only is a meticulous scientist, very good at math, but she's also a very good friend, a very good runner, and she has 2 black belts in karate in 2 different disciplines. So, keep that in mind. Kim has been very productive in terms of intellectual output. She finished her PhD at Princeton with Matt Botvinnik, and she moved to DeepMind where Matt is, and she's still there as a research scientist. She was on some 30 under 30 innovators in AI list. I remember, I should mention that. And she's been also mentoring other grad students now that she's a research scientist at DeepMind. I am a very big fan of her work. I always enjoy discussing with her basically anything, especially science. I really enjoy reading her papers. I really enjoy discussing when we are at the idea stage, or if I see a new paper. I think that everyone in science should have a Kim. And with that, Kim, if you'd like to share your slides, we would love to hear from you. And of course, if John and Jovo have anything to say.
Okay, unmuted, press and play. Cool. Okay. Thank you for that completely heartwarming introduction. Every time Ida introduces me somewhere, which has been like a couple times now, I'm completely chuffed and red by the time I start my slides. So thank you very much. My name, as you all know, is Kimberly Stachenfeld. I'm a research scientist at DeepMind now, and I work on the neuroscience team. My research involves roughly equal parts machine learning and neuroscience, and I'm broadly interested in the problem of how humans and animals learn structure about the world and use it to rapidly solve new problems. And then the machine learning side of that is how do we get machines to do smart stuff like that too. So to start out, we have early evidence that animals learn structure about the world, even when it's not immediately rewarded, from Tolman's early experiments with rodents in mazes. Among other things, Tolman is famous for introducing the term cognitive map, which captures this idea that animals learn structure about the world and iterate over this structure, reason about it to ultimately produce sophisticated behavior. So a few decades later, it turned out that this cognitive map idea had an unexpectedly literal neural correlate in hippocampus. O'Keefe and Ostrovsky found these cells in hippocampus that they called place cells. They fire selectively when the animal's in a particular location in space. These plots on the left show the location of an animal and the firing of one particular place cell at these different locations. And then in entorhinal cortex, which is connected in a loop with hippocampus, these cells called grid cells were discovered that also have spatially receptive firing. They fire for particular locations in space, but as opposed to the sparse selective firing of place cells, these have multiple spatial fields that are compactly arranged in this hexagonal lattice. So more recently, we've started to unpack the broad variety of the things that these hippocampal and entorhinal cells do. And we're seeing that they're not just for physical space. So for an example, in a task where a rodent heard a rising pitch, these cells that were place cells in other environments would encode the pitch of a sound in this particular task. And pitch, of course, is the relevant state for solving this task. In a very different style of experiment, humans were shown morphing bird patterns with 2 dimensions of variation, their leg and their neck length. And with fMRI, it was shown that you see grid-like representations in this leg times neck space that tiles the relevant feature space. And also in these other environments like virtual reality and visually fixating on an image, you find these grid-like representations for these tasks that have somewhat spatial-like structure, but aren't exactly spatial navigation. So it starts to get even more interesting when we see that these cells are not just for physical space and not just for tasks that resemble physical space in their underlying structure, that have planar Euclidean geometry, but also in these tasks that are better represented as discrete task spaces, may be described as a graph or a network or a Markov decision process. And in these tasks, we see hippocampus at least encoding what seems to be like a discrete state index. And this is consistent with ideas that maybe the hippocampus is representing a cognitive graph that's connecting states in an arbitrary and flexible way. And this closely related conceptualization that hippocampus is representing relations among memories. In more RL terms, you might think of hippocampus as representing specifically the transitions between different states that are possible, which also can be applied to discrete or continuous spaces alike. So from a normative perspective, purely, I think this idea that hippocampus represents discrete spaces as well as physical spaces is really interesting. On the one hand, it gives us a lot of flexibility. These types of representations of structure are very flexible. Instead of the constraints that geometry gives you, or Euclidean geometry, you can represent arbitrary relations between different states. You can build very bizarre graph structures. On the other hand, I think it can feel like these models are throwing a lot of structure away. Animals need to navigate space quite a lot, and spatial environments give us a lot of structure that can be useful for generalizing. The relationship between 2 states at a constant displacement is the same no matter where you are in the plane. If you zoom in and out, Euclidean space has the same structure. If you rotate your environment around, Euclidean space has the same structure. And getting rid of this ability to generalize that geometry affords us means we have to learn a lot from scratch in each environment. That's not necessarily great. So I think coming from a normative perspective, we want to think, how can we get both? How can we get these expressive environments that capture this range of data that hippocampus is involved in, but still preserve some of the generalizability that geometric representations get us, and also capture the spatial specificity of some of these representations? So that's going to bring us to the reinforcement learning framework. The reinforcement learning problem is, given some task, you want to learn a policy to maximize your expected cumulative reward over future states by trial and error. It's a really general framework. We can apply it to lots of types of problems, and that's one of the reasons it's useful for us here. You could apply it to problems like chess. You could describe a more abstract problem like cooking, or you could apply it to spatial navigation, and the states you can occupy are locations, and you want to maximize the number of Fruit Loops you eat. The issue we run up against is that reinforcement learning can be very hard in complex problems. RL in its natural formulation throws a lot of information away. If you're only learning about reward, you're discarding other information about patterns in the environment. And there can also be a lot of states to learn about, which is especially challenging when reward is sparse, as it is in this little Fruit Loop maze. So one of the questions we want to ask is how the brain learns and represents structure that can support more efficient and flexible learning in the reinforcement learning context. And this kind of harkens back to this idea of how do we get the flexibility of these graph-like or model-based representations, and also the efficiency of spatial generalization. So a cute example that I like of what makes model-free reinforcement learning inefficient is this example of what might happen if you're doing a prediction error-based learning in a discrete Y maze. So I'll describe that. Basically, you start off in this discrete Y maze. Each circle represents a state, and you start off in the center. And as you wander around the environment, you eventually find that this top left corner has a fruit loop in it. Of course, you don't know what top and left are. You just know these states are connected. But you say, hooray, I guess this state over here is rewarding. Later on, you discover that there's a state that predicts this rewarding state, which you didn't remember before because it wasn't rewarding at the time. And as you traverse the environment, this reward information eventually propagates back to the beginning, and you ultimately can conclude, I should go left. And this maybe seems a little bit cartoonishly silly, but it's not a far cry from what model-free algorithms do, sometimes really powerful and scalable ones like DQN. And if you have a lot of data and you have a lot of time, there's really no reason not to do it this way. It's very agnostic. But to humans, I think, and maybe to animals too, a more reasonable thing is to organize your states. And the first time you see a fruit loop in any part of this arm on the left, say, I should just go left in the future. And you could come up with a similar rule for multi-compartment environments. So this is kind of one of the reasons that a representation of your environment can make learning a lot faster. Instead of learning about one state at a time, you can learn about a whole bunch of states. But of course, in other environments, it's not necessarily so obvious how you should organize your states. There might not be room labels when you walk into a room. So we can break this down into the two questions we had about improving reinforcement learning. One is, what should we learn in addition to rewards so we're not throwing away too much information? And the other is, how can we make it generalize? And this is one of the things that geometry can afford us. So one answer to the first question is that you want to learn predictions in general. In addition to predicting what reward is going to happen next, you want to try and predict other things that might happen next too. And then no matter what your reward turns out to be, it'll probably be a special case of the set of things that will happen in the future. There's been a lot of work on this. Here's some that I listed in case you're curious to follow up, but it's definitely a partial list. And these all represent different approaches in machine learning to learn a predictive representation and try and use it to solve problems very flexibly by having represented more structure than you needed off the bat. An answer to the second question might come in the form of compression. You want to learn as short a description as possible so that when you learn about one state, you learn about all other states with an overlapping description. And so one thing you could do is compress the predictions you're going to make, and then you've basically said two states that predict similar things will have an overlapping representation. Rather than list specific works, I really listed just like fields of compression that capture this idea of compression in a different way. Dimensionality reduction, clustering, segmentation, they all formulate compression in a different way, but have this underlying goal in common. So we had this paper out a little while ago that was suggesting that this breakdown of representation learning desiderata does a good job describing what's happening in the hippocampus and in the entorhinal cortex, and suggesting that maybe place cells and grid cells are therefore participating in forming a representation of the environment that can support efficient downstream learning, but also can be applied to a more general swath of problems than simply navigation alone. That physical space is one example of the type of structure you might be able to capture. The specific models that we use to do this, I won't go into too much right now because I want to talk about some other stuff in a short amount of time. But we used the successor representation as a predictive model of what states could happen next. This is a pretty, in some ways, minimal model where you're simply representing every state in terms of the number of times you can visit other states in the environment. For grid cells, we used an approach which was taking the eigen decomposition of this successor representation. So basically using eigen decompositions to compress the predictive information. And the particular math of taking eigen decompositions of matrices like the successor representation turns out to have a lot of theoretical connections that are really interesting. One of them is that it's involved in spectral clustering, so that gets us a little bit at the clustering aspect of compression. And another, I think, that's particularly interesting in the context of hippocampus and entorhinal cortex is that these eigenvectors can be used to generalize geometric concepts to graph structures. So if you want to talk about how translation or increasing your scale could be applied to a graph, you can use these compressed representations to describe it. And that's a field called graph processing if you're interested. So we sort of ended up finding our way back to geometry and metric representations, which I think is kind of lovely. So another thing that we did with the these eigenvector representations is relate them to relational deep learning. And that's the thing that I'm excited to finish off with. So relational deep learning is basically the problem of how we can apply deep learning to relational problems, or problems that are expressed as a graph or a network. And again, this is a really general description that can be applied to lots of different types of problems. You can describe molecules as nodes that are connected by bonds, where the nodes are atoms, mass spring systems, certain physics problems, even language can be described graphically. And we want to apply neural networks to reason about these problems. So one thing that I had been interested in when I started working on machine learning problems from neuroscience is how we could apply these ideas about hierarchy and geometry to graph neural networks. So this is an illustration of what's happening in a certain type of graph neural network that comes from this really lovely review by Peter Battaglia and a bunch of other authors as well. Basically, a series of neural networks are used to update nodes in the graph as a function of the underlying graph structure. So basically, you have one state or node in your graph. It has some description. You pass it through a neural network, and you send it to all of the neighbors it's connected to, and you keep applying this iteratively until you end up producing a result to your computation. These operations work very locally, but there's been some work on applying hierarchical math to make these more efficient and to make them generalize better. One example, which this illustration comes from, is a diff pool model by Ying and colleagues. So we wanted to use the same eigenvector math we had used as a model of grid cells and see if those were a good way of doing hierarchical assignments. Basically, instead of the particular clusters that an algorithm like diff pool would use, each node in a high-level graph would correspond to one eigenvector. And it would be used to represent coarse-grained information about the inputted graph. So basically, you have some graph that you're going to put in, you filter out very coarse-grained summary information, and you send it into a smaller graph net that will reason about it. You iteratively apply this process until you get an answer. Very broadly speaking, since I kind of wanted to use this as an example, but knew I wasn't going to have time to go into it, it's a particular hierarchical model that uses the connectivity as the basis of its hierarchy. And we found it helped on some set of problems and didn't help on others. Basically, we found there were some cases where the performance improved and some cases where it didn't. We found there were some cases where efficiency improved and some cases where it wasn't. And we found that there were some cases where we improved our robustness, but not overwhelmingly. So we were really excited about this in some sense. I mean, it was like doing something, and we were curious what this model would do. But on the other hand, we were sort of left feeling like hierarchy, or at least the hierarchy we were using, was only hitting glancing blows at this problem, that we weren't really seeing an astounding improvement, and we weren't categorically fixing everything that we wanted to do. And I think, maybe some part of this is that we could have been using a different hierarchy. Maybe a different hierarchical organization would be better suited to these problems. But I think that I also had very unrealistic expectations of how much hierarchy would help that maybe don't apply to this type of problem. And I'll kind of describe what I mean. And this is the part that I haven't really presented before, but since we're supposed to present things that might be good for discussion, I'd really like to get feedback on this. So I sort of was thinking, why did I have such high hopes for hierarchy in the first place? And what was I expecting to see? What would have counted as impressive to me? And I started to think that maybe supervised learning problems in general, the kind of prediction problems we were using, didn't leave space for hierarchy to be interesting. And one of the reasons I like hierarchy, it's not that it's motivated by the problems or that I'm working on specific problems that really require hierarchy as a solution, but rather because a lot of examples of interesting and intelligent behavior by humans and to some extent animals seem to apply hierarchical abstractions in a very creative and compositional way. So I have this kind of underlying faith that hierarchy is going to be really important and interesting because of examples like this. So one example, this was the figure that I had on my opening slide, is Da Vinci's dragon recipe, where he says to draw a dragon, you take for its head that of a mastiff, eyes of a cat, ears of a porcupine, nose of a greyhound, etc., and you compose these all together to create something that looks like a dragon. It's very imaginative, very compositional. Another example that's a bit more, like emotionally salient and stressful is this drawing that I found in a book of a child who illustrated the things he saw at 9/11. He had a very traumatic experience seeing the Twin Towers, and a few days later illustrated what he had seen with added safety precautions that would keep some of the more traumatic elements of his memory from having happened. And both of these examples in their way demonstrate a kind of innovativeness that's very counterfactual and compositional and creative. They're recombining elements to create something fundamentally new. There's no space in anything that, in really the model that I made or the benchmarks that we tested it on, to implement or test for that kind of creativity. So I was thinking about this at one point and started drawing this open-endedness spectrum that I was hoping to use to get insight on what kinds of problems might be interesting applications of hierarchy. And on the left-hand side, we have these problems where the solution is concretely specified. These are all supervised learning problems where you have a target you're trying to match, a lot of machine learning benchmarks, most navigation problems, and some reinforcement learning problems too, ones that are maybe really simple or have only one specified solution. At the other end, you have these domains where we certainly have evidence of creativity, but there's no solution specified or a solution barely specified. And maybe art is something in this category, although I'm scared to have a strong opinion on what art is. And maybe things like generative models and unsupervised learning start to get into this area because these models are trained on minimizing reconstruction, but when you sample from them, that's an objectiveless process. You're turning random noise into an output. And it's more generative than it is optimal. And in between, we have these problems that are, I would consider open-ended, where you have a solution that is loosely specified, but many ways to satisfy it. And this seems like where there's a lot of room for both creativity, but also something that could tell us whether our models are doing a good job or not. And I wrote this down specifically when I was working on a construction project with Jessica Hamrick and some other authors as well. That's what this citation is. And I was thinking, like, one of the great things about this domain is perhaps it has room for these open-ended problems. There's many ways to compose architectural elements like doorways, walls, stairs, etc., and many different design desiderata you might want to simultaneously optimize. I think some reinforcement learning problems and engineering problems have this quality as well. And basically, I mean, this comes down to, I think, the benefits you can get from hierarchy are at best efficiency in these more constrained supervised learning problems. And something that is maybe more inventive or more imaginative or creative really requires a different type of problem. This is related to this idea of the problem you'll hear people talk about in machine learning, which is basically the problem of coming up with tasks that either demonstrate or require real intelligence in a way that humans would consider it like meaningful and satisfying. So to close, I wanted to bring it back to these cognitive map ideas a little bit, albeit somewhat tenuously. I think one of the things I was struck by, or have been struck by for a long time, is just like the sheer number of very cognitively interesting tasks that hippocampus is specifically involved in. All of these tasks all of these functions that I listed are things that are at the frontier of open problems in machine learning. And hippocampus seems to be a convergence point for a lot of them. So I think there's broadly a lot of potential for bridging neuroscience and AI, and that it's possibly relevant to understand these areas to think about how we might implement solutions to open-ended problems too, which I think are really qualitatively different from a lot of the stuff machine learning has worked on so far. I think there's also added motivation for hypotheses about hippocampus that go beyond spatial reasoning. But I think the versions of representation learning that are very dominant, that I've been thinking about a lot, prediction and compression, are not sufficient. And these ideas that others talk about compositionality, counterfactualness, are really key to moving forward. So on that note, I want to thank my collaborators and welcome any questions and an extended discussion period. Thank you very much.
Thank you, Kim. That was a fantastic talk. There was a lot of things packed in there. It was very exciting.
Yeah, it was. I was maybe overambitious in the things I tried to shove in there.
Oh, in the best possible way. I absolutely loved it. So I think that it would be helpful if I keep my questions for last. And yes, so people are appreciative of your talk also. I think that I would love to hear questions from Jovo and John first, and any clarification questions they might have, especially to just unpack the wonderful talk that you gave. And then I'll ask my sort of more specific questions. So I think John is unmuted, so John might be first.
Oh God. So this, Kim, I don't have loads of questions, but I always find in a meta level these talks very interesting, and I think the conclusion at the end of your talk was there's a lot of hope in the hippocampus. It is very interesting how it seems to perhaps be a key to some of the other cognitive operations you talked about. And then, of course, you start with RL. And, one question I have right from the get-go is, would it be fair to say that these additional things like the art projects and the other cognitive things, you think will succumb to a combination of RL and glimpses at the hippocampus? Is that where the answer to cognition is going to come from? Some mixture of RL and hippocampal properties? Where does that kind of single-minded approach, why is that going to win? Is the answer.
I think, yeah, I mean, that's a very interesting question. I mean, I think that the thing that I like the most about RL is that I think it sets up autonomous learning in a very nice and clean way. It's basically like, we're not going to tell you what the answer is. We're going to tell you how good things are, and you can wander around and figure it out. So I think that's a really nice way to motivate some of the challenges with autonomous learning. I realized like a little while ago, I've actually done very little work on actual reinforcement learning at some level. I think that reinforcement learning, as it relates to the stuff that I've worked on, has been largely a motivation. Like there are some, if you just do it off the bat, you get autonomous learning, but you get extreme sample inefficiency. And it doesn't, it doesn't provide a way to solve these problems. I think it's a nice way to motivate. We need to come up with more compact ways of representing the environment and compact ways of reasoning about the environment. Otherwise, RL is going to take a really long time. But I'm not sure RL is necessarily a crucial element to this aspect of considering the question of like, what is an efficient way to support reasoning? I think it's a good motivation, but isn't strictly required. It is really required if you want to think about motivated behavior and how rewards drive behavior. That's like very close to the heart of what reinforcement learning is. But I guess I think for a lot of these problems about how to get very intelligent or very creative behavior, it's not necessarily just an RL problem, but it's really like, how do you come up with a compact way of organizing your environment to support efficient RL, but also maybe efficient exploration or creative compositions of new stuff, new ideas.
Side comment, exploration and composition are also elements in RL, and the way that you yourself use RL is not just based on rewards, it's actually based on representation learning. So just want to, yeah.
Yeah,
so just, okay, sorry.
No, that's all. I mean, yeah, so I think this is another way, like reinforcement learning invites space for these problems. It's a good motivation. It has like space for exploration, and you can benefit from exploring your environments efficiently in a very quantifiable way. I think this is a great way of setting up autonomous learning. You could talk about exploration without using RL maybe, but I think it's a very succinct formalism for fitting it all together and anchoring it to a normative objective. Yeah.
So just to continue on that, autonomous learning, I mean, most of us get taught by others how to do things, and it's transmitted by culture and by language. So given that we'd be helpless without being taught stuff and semantically informed about stuff, why all this emphasis on autonomous learning?
I think that the emphasis focus on autonomous learning largely comes from this idea that we want to learn things about the world that we didn't already know. And I think that's, yeah, I mean, that's, I think you could maybe, you could make, I think, a very good argument that that if you wanted to get a very intelligent machine, you should come up with ways to teach it everything that humans know. There's a lot of people working on this. I think it has a lot of promise. One of the things that I find particularly compelling about autonomous learning, or some way to set that up, is I really like this idea that machines could learn something that goes beyond the stuff that we already know, and in some ideal world, certainly not the current world, but maybe beyond the biases we have, and besides the current way that we've broken down problems and the way we think about things. I certainly wouldn't want to say that machine learning is free from the biases we have. It if anything, really like cauterizes them. But I like this idea that we could use machines to come up with, to learn things we don't already know.
And my final question, just about knowing, right? So I think I saw you at Cosine give a great talk in Lisbon, and you showed the sort of V-shaped maze, and then how silly it would be to do it model free and cluster the left arm, and but to me that's still, if I'm understanding it, the way that works out. For example, with the successor representation and probability of states from one state, and stuff you've done and Ida's done, but it's still a procedural algorithm, right? But that's not the same, if I understand, by going, oh, that's a corridor and I just need to go left, right? It's a V shape. So I guess it's a question that Ida and I've had conversations about over the months is, would you agree that going, oh, it's a V shape with a corridor, that's different, isn't it, from procedurally discovering structure? Yeah.
So I think what, sorry, do you?
So I just want you to know, isn't there a third way? There's model free, and then there are these other ways, which, successor representation somewhere between model free and model based. And then there's this thing where I can just go, it's a corridor. I just need to go to the end. I don't have to discover any structure. I know what a corridor is, right? What is that?
Yeah, so I think there's a couple elements in there. I mean, one thing that that I think is the first big point of that is this quality of recognition. I've already seen this structure before. I do not need to learn how to organize it. Rather, I just need to recognize this structure is organized the way whatever the last thing I saw.
Or having never seen it before. You just got told it's a V-shaped hotel with a corridor in it. You just get told. You've never been there in your life.
But I do know what V's are in this hypothetical, right?
Yeah.
Okay. Yeah, I mean, I think, so, okay, in that case, there's like two main components. I mean, one is this recognition of like, I know what a V is and I can apply that again. And then the other is this incredible abstraction where you go to, I know what a letter V is and I can turn that into a maze that is shaped like a V. Presumably I've had some experience maybe translating maps into like actual navigational experiences. So I know what that abstraction process looks like. I know what that vector from the illustration space to the navigation space looks like, and can apply it again. I think that's really the problem that we'd call like transfer in machine learning or reinforcement learning of I've done this before, or I've done something like this before, and I can now just immediately behave in this context now because it resembles something that I already know about. And in addition, this other element of overcoming a pretty large abstract barrier, where you're going from something written down to an actual like experience of putting one foot in front of the other. And that's definitely really different from the problem of organizing this information from your direct sequential experience, right, which is maybe more native to the to at least the RL problems we normally think about, although not the broader formulation of RL.
So just given that, do you think we're going to need an additional framework? Or is this sequential decision making, as you said, going to do it? And I'm just trying to put you on the spot here. Are we going to have to do something qualitatively different to capture this odd ability to do these bizarre abstractions on the fly?
I think that I mean, probably the answer is yes. Although I think at the first, but a safe answer would be, yeah, we'll need more things because we haven't solved general artificial intelligence yet. But I think for this specific question, the question is like generalizing the notion of relation. So two things being adjacent in time is one example of a way things could be related. Two things being adjacent in space is another way. So in this V example, there's not an aspect that you're temporally traversing a letter V. You look at the V, you perceive the V in parallel, according to everything I know about vision. And you have relations between points on the V, but they relate to visual locations in space. If you want to translate that to how you will experience things with time, that is basically like translating it to a different kind of relation. Maybe like a similar one, because locations in space in the maze are related to locations in space in your V, are related to the locations in time that you will now perceive because you're constrained to navigate space in time. But I think for this, the key question is coming up with a more general conception of relations. And it's really open, I think, how those are going to relate to the kinds of relations that we think hippocampus is representing. If hippocampus is doing something extremely, maybe more general in spatial navigation, but still something extremely episodic, then we would think that maybe sequential states in time will be privileged as a relation. But there's also theories like Eichenbaum, Tim Behrens have talked about these, that more general relational maps are represented in hippocampus that aren't necessarily related in time, but have some sort of abstract feature representation.
Thank you. Awesome.
Yeah, great, wonderful questions. Very enjoyable.
I like that. I know what question John's going to ask now, because it's that one, basically. That it's a deep question that comes up a lot, so it's always fun to hear different people's perspective on it. So I had I guess somewhat related question to this. I read your Hippocampus as a Predictive Map paper, which I thought was really beautiful, actually. I really liked, the way I think about representation is very different from the way you propose that I think about it, basically. I think of it, and the way I learned about it is my brain represents kind of the stuff out there. So motor cortex represents where my arm is, the angle of my joints. Visual cortex represents where stuff is, and then hippocampus represents kind of where I am. And you propose this other thing where the representation is different. There's a successive representation, and there's value involved, and there's rewards involved. And I just wondered, you talked about this model of the hippocampus, and you gave some really compelling data showing what an intriguing model it is for fitting a variety of different hippocampal data. I just wonder how far you can push it. Like, does this idea of successive representation, does it transcend beyond hippocampus? Like, will that do a better job for describing motor control as well? Because people in motor control fight about, is it force or angle or velocity? And here's just another thing that maybe it's successive representations for that too.
Yeah, so I think the first, can you guys still hear me? Okay. Yep. Sorry, the static in my ears went away for a moment. Yeah, I think this question about what does representation mean is a really interesting one. I think in the way we meant it in that paper, and in the way it comes up in the representation learning literature and the reinforcement learning literature a lot, is how do you represent the world so as to support some downstream process efficiently? It's very much like, how do you represent your inputs? And I think maybe more traditionally, and I think more the view you were describing, is that it represents some quantity in the world. That's the neural representation of some quantity in the world or in your body, and it's recapitulated. It's more like, it's a bit more upstream. It's like, how do you represent these things so that they capture the world, rather than how do you represent these things so that some efficient process can operate over them? So I think that idea is probably pretty general and could be applied to lots of different things. This idea of like, how do you support a computation efficiently as a question of what your representation is doing? In terms of the generality of the successor representation idea, I think it's definitely possible. I mean, I think that the in its purest, in its most abstract form, maybe the successor representation is one example of an algorithm that makes predictions about what's going to come next and summarizes them in the instantaneous activity of neurons. So there's other kinds of predictions that are not well captured by the successor representation, such as sequences, which Ida has worked on a lot in integrating sequential models with successor representation models. So even for hippocampus, there's types of predictive activity, like these sequences, that the successor representation doesn't really talk about. The successor representation is more like how are predictions captured in the receptive fields of a neuron. And so, yeah, I think this idea that predictions are happening all over the brain is probably very general, and lots of people have talked about that in the course of neuroscience. And then also these maybe trade-offs or these cooperation between sequential styles of prediction, receptive field styles of prediction, and maybe other kinds of predictive models too that I don't know about or haven't thought about. I think that's probably going to be a pretty general concept, and certainly applicable to like predictive motor activity.
Cool.
Yeah, I hope that answers your question. It was a little meandering, but
No, it was interesting to hear your perspective on that. Ida,
I have questions, but I just want to say to that our previous guest, Sam McDougall, he actually has thought a lot about the relationship between successor representation and motor learning. I think John Krakauer as well. So that was definitely something that I've seen before. So as you know, I would have a lot of questions, and I really loved the new stuff that you had. But because we have 16 questions already, I'm gonna I think I'm just going to try to ask them in a compact way. So I'm giving you the Eigen decomposition of my questions. Hierarchies in the brain. So it's not just the hippocampus that either processes or represents hierarchies, and John left, okay. Can't stand this anymore. Especially an important aspect of the kinds of representations we find, and we have some papers on this. Okay, we have John back. Is the prefrontal cortex, where we do see also the sort of predictive representations, especially at higher scales of abstraction. So we know that there is some hierarchy along the long axis of the hippocampus, but it doesn't go too far, and there are other parts of the brain that seem to collaborate with this network. Even grid fields are observed also in the prefrontal cortex. So I do wonder, first of all, your last slide, I think it was giving too much credit in the credit assignment to the hippocampus, because, you know, when hippocampal patients lose their hippocampus, it's true that they can't learn new maps, but they can still be creative. You know, they don't lose all of the ability or compositionality. They don't lose all of the abilities that you had on that slide. So I wonder whether we're giving too much credit to medial temporal lobe. And you know, whether it's important to mention the hierarchy, the hierarchical representations that the hippocampus enables in relation to hierarchical representations across the brain. And then another thing that I wanted to ask you is a follow-up to the NeurIPS discussion that we had. So I'm just going to give you a minute to respond to this before I ask you that one.
Okay. I think that's super fair. I mean, I think that I'm definitely guilty of being overly hippocampus centric in the way that I think about things, because I've studied hippocampus way more. I think I mean, I guess the thought I've had, the thing I found striking that I wanted to allude to on my last slide is hippocampus is involved in a lot of stuff. And it's particularly involved in a lot of these very rapid behaviors, like rapidly acquiring new behaviors and rapidly updating what you're going to do. It's definitely not, you know, the rest of cortex is not like keeping the hippocampus warm. It's definitely a bunch of really sophisticated stuff is, of course, going on at PFC. That's like the famous home of sophisticated stuff. And then I think there's these hierarchies in other parts of the brain have been well established. I've seen your papers on it, and certainly, like, yeah, hierarchy is not unique or even like maybe principal to hippocampus. Another example I think that I like illustrates this divide to me a lot is like with a longitudinal axis. I think one way to think about it is that it's grouping things by spatial scale or temporal scale, that you get coarse representations in the ventral hippocampus and sparser, smaller ones in the dorsal. And the hierarchy you get in vision of like objects in inferotemporal cortex and like low level inputs in V1 is a completely different hierarchy that we would think is roughly factorizable from the hierarchy in hippocampus. There's, you know, with PFC, it's more complicated because that kind of hierarchy overlaps a lot with the kind of hierarchy we think might be going on in these other regions too.
But there are some hierarchies in the prefrontal cortex that don't correspond to earlier cortex also, or earlier places. It has its own kind of hierarchy of task sets, for instance, and things that require multiple regions to be sort of implemented. So the thing that I wanted to say, ask next was about compact representations of the successor representation. And I touched on this at the discussion after your talk at NeurIPS. So this would be a follow-up. I think that was a wonderful discussion, and I would love, maybe we have a little bit more time now. So the successor representation itself is a matrix, the way that we think of it, or we show it in our papers. And that's, if you have n states, it's an n by n matrix. And this kind of, it's not computationally, it's not sort of representationally super efficient to store n squared items for n states that you observed. And so there is a requirement, of course, that we discuss what is the best way to represent the successor representation that's efficient, not just linear order, meaning n for n, but hopefully maybe better than that, maybe log order or something like that. So we discussed a little bit before what might be the different options. It would be, and especially the role of the internal cortex and compact representations there, and the eigenvectors or basis sets in helping with this kind of more efficient representations. So I'd love to hear your thoughts on that. And I wish Tim Behrens was here. He would have had a lot to say about this.
Yeah, he definitely would have. I really liked that conversation at the NeurIPS workshop because answering it, I realized something I had never really like articulated to myself before, which is the nature of compression that eigenvectors do is that they represent the information in a matrix, which is n by n, as succinctly as possible in a vector, which is just n by 1. So for instance, if you have a bunch of states that are arranged in a line, like state 1 connects to state 2, connects to state 3, etc., and you start randomly walking over this environment, you will get a matrix of how these states predict each other that's in some sense massively redundant. It has a low rank structure and can be represented as an ordering of the states from 1 to n. And this is roughly what the first or the second eigenvector will give you, is this like change in, at one end there'll be +1, at the other end there'll be -1, modulo the normalization constant. I think that this is one way to maybe think about this compression as we've put it up in our model, is that you can take the information about how states predict each other, and that's represented in hippocampus, we think. And if entorhinal cortex is compressing this effectively, it has cells that are trying to succinctly represent the global structure that is common to the predictions in this environment. There's shortcomings to this compression method, and there might be ones that are better optimized to specific environments. If all of your environments are spatial, maybe you want to just use like relative locations in space as your environment. If all of your locations are clustered, maybe you want to apply a more selective specific clustering algorithm. This is sort of like maybe a somewhat general purpose algorithm for compressing things. It's not the only one. The other thing that this is limited in, but also all compression algorithms I think are limited in, is handling directed environments. So if you go from A to B, but not from B back to A, that's a pretty difficult thing to summarize in a compressed way, because you don't want to have a representation where B is close to A. That's not, that only captures one side of the story. You want B to be close to A, but A not to be close to B. So you can't really represent that with dimensionality reduction or like a geometrically succinct representation. It violates like the structure of metric spaces. So for that, maybe you need to represent it as an exception or an absorbing state or some other, fancy method that I don't necessarily know about. Yes, please.
I think you can represent that fine if you use complex numbers. It works out.
So I think for for the environments we simulated that are like rotational environments, and you're just always going to the left, or you have some rotations built in, you can get those okay with complex numbers. For environments where you're always going to one state, we got these degeneracies where you just have like 1 at the location where you go to and 0 everywhere else, that it kind of closed in on itself. So I think, yeah, that there are different types of asymmetries there. Does that check out?
Yeah, that makes sense.
Okay, yeah.
Yeah, and
That's a good point, though. It's not just as simple as directedness.
yeah, I think that there's something interesting in that eigen decomposition is still at best order n. It doesn't get better than that. Like, I think there might be still nice ways to represent the SR in compressed ways, but I wonder whether one could find some combination. I think, and this is where I guess Tim Berenson's perspective, I think it might be interesting. I hope I'm not misrepresenting his view, but I think the basis sets, if there are particular basis sets that they're there already, then you could have, and you could sort of approximate the compression with some combination of those basis sets. You might get away with a little better compression, but it will just get more complex. So you might need some working, some online processing time to translate your compressions into some function of those basis sets. But once you do that, you might achieve even more compression than order n, which eigen decomposition gives you.
Yeah. So yeah, I mean, again, eigenvectors aren't like, necessarily the best or only way to do compression. But I think where the n comes from in the eigen decompositions is going that you have like, you might just have one eigenvector that represents many states, and so that would correspond to like one grid cell in our model, but you still have all of the synapses to that eigenvector that say like, what state am I in, map it to a firing rate. If you in the multitask setting, in the single task setting, there will be some compression that's going to be more compact and will be made less compact for that one task if you try and make it work for multiple tasks. So I think with Tim Berenson's stuff, and I think what you're alluding to is, if you have many different tasks, you don't need to learn a task-specific compression that might be the most efficient for one task, but it'll start to get really inefficient as you want the same. If you get one task representation for task. So you might be able to compress the entire set of tasks you have with a compression scheme that is overall more efficient. For any given task, it'll be less compressed than the specialized compression would have been, but is more compressed than one compression per task. I feel like there must have been a more succinct way to say that, speaking of compression.
I think you said it beautifully. I really enjoyed the string of words that you just put together. So one last thing before we move on. I wish we had more time to spend on spectral GNNs and the way that you think that the way in general that you think spectral clustering, the way that it is enabled by using eigenvectors of the successor representation or eigenvectors of the graph Laplacian, the ways that you think that that kind of clustering can correspond to certain structures in the brain, the way that certain hierarchies of neural networks are structurally connected in the brain. So it seems like it might have been some kind of a pressure to come up with some kind of a compact hierarchical representation of the world, and that might have shaped the neural architecture of some parts of the brain. And I think that that's a direction that we haven't really explored, the kinds of pressures that might have enforced a particular architecture in the brain rather than other, or a particular combination of certain kind of modular architectures in the brain. And it's a more speculative, of course, approach, but I wonder what you think of that.
Yeah, so I think one thing that speaks to this and is like been around for a really long time is the efficient coding hypothesis, which has like a pretty specific reason for representations to be compact and efficient. This idea that like it's metabolically expensive for a lot of neurons to be firing. So the brain is trying to represent the statistics of the world as it relates to the statistics of tasks it's trying to perform in a way that minimizes firing rates. You don't have a bunch of neurons firing willy-nilly unless they're doing something necessary. And either correcting for errors or efficiently representing the world. I think another efficient idea that's like really closely related and leads to mathematically similar ideas is that and there's an evolutionary pressure for humans and animals to make quick decisions and make the right quick decisions. So for that, one, at least this like representational idea is that you can do this by having overlapping representations for things. So one reason to use overlapping representations is not necessarily just so that you don't have the metabolic cost of lots of neurons firing, but rather because having overlapping neural representations for things that should evoke overlapping behaviors will cause you to generalize and behave really efficiently. So this is kind of like more of a sample efficiency hypothesis than a metabolic efficiency hypothesis. But that's, I think, one thing that would lead to like some amount of like compression and modularity and representations. Yeah, I think you had Jane on a little while ago, and she talked about meta learning. So certainly, like representations or neural pathways that support multiple different behaviors, distribution of behaviors, can be formalized and used as a motivational explaining force.
Yeah, thanks for that. And so the efficient coding hypothesis, unfortunately, I don't think it gets us very far in this regard. But I think that we should, hopefully, we will see a little bit more of representation learning as a pressure for the development of the architecture or the evolution of different kinds of architectures in brains. I think that's something that at some point it would be fun to work on, especially since my favorite area, the prefrontal cortex, seems to be more on that side of things. Its architecture seems to be initially just messy, but the further you go in the species, it seems like it becomes a little bit more sophisticated. In a situation where in humans it's sort of it's the largest, and it becomes a very crucial area at the cost of other areas being smaller, including the visual cortex. So yeah, so I think that there's a lot to be said there. I wish I could ask more questions about the spectral geometry, but I want to move on because it's now 5. I want to move on to the currently 18 questions. So I want to invite everyone, if you have questions, please put it in the Ask a Question area and vote on each other's questions, and we're going to invite the highly voted questions. Jack Lovell is our first highly voted question. Is Jack here? Does he want to be online? Jova, do you want to invite Jack and Adam Shai and Melanie? So these are our first 3. So whichever one of them accepts first.
Well, while we're waiting, I'll just say I really liked your being really clearly about the difference between sample efficiency and computational efficiency or metabolic efficiency. And I think I totally agree with you that the motivation for efficient representations, it makes much more sense from a learning and sample efficiency perspective, particularly because I think spikes are not that expensive as compared to building new synapses and maintaining homeostatic equilibrium to maintain them. And so even from the perspective of metabolic efficiency, I think it makes sense what you're saying.
Thanks. Yeah, I think I really like the efficient coding hypothesis, but I've always found the metabolic efficiency, yeah, I guess a little bit unsatisfying. I think partly because I guess this more like immediately relevant to maybe the stuff I was thinking about reason would be that you want to have this sample efficiency effect. I mean, then later I learned, like, the brain does take a lot of metabolic resources. Maximizing its metabolic efficiency is not nothing. But I think that makes a lot of sense, and is not something I realized, that like the efficiency, the metabolic cost of spikes is just not significant relative to the rest of the stuff the brain's doing. We have 2 new guests.
Yeah, so Jack, do you want to go first with your question?
Sure, yeah. Thanks, Kim, for the talk. That was really great, and thank you to the organizers. My question was that I was wondering what happens to a cognitive map when an agent is uncertain about its environment, and that is an agent still able to abstract a discrete representation? If so, are there simply just amounts of uncertainty associated with each state, or is there sort of a deeper way of thinking about a problem beyond just associations?
I feel like you were planted here by Jesse Gertz, who's a student I've been working on adapting the successor representation model to the probabilistic setting. Yeah, I think, yeah, so the way that Jesse has formulated this problem is that you have, that you're still learning a successor representation as your token predictive model. But you use a Kalman filter to represent uncertainty about which states are predicted. So this basically, whereas the successor representation is a point estimate, you're just representing the average number of times you'll visit every state. This learns a standard deviation and covariance structure among these representations as well. So you basically just have some uncertainty over which states will come next. And you use that to inform your behavior instead, and then it downweights predictions when you're less sure about them. Another ingredient that's part of this model and made it apply to a much broader swath of data is including a term that's uncertain about your context as well, which I think was another element of your question, which is in addition to having uncertainty about what states are going to come next, you might be uncertain about which environment you're in the first place. And you can learn a different predictive map for different contexts in the way. So this is one way to set it up, that you have multiple maps and you're uncertain about which one applies. One other thing that we haven't added in this, but I think some other work, maybe James Whittington and Tim Behrens speaks to this a bit, is if you think you have familiar ingredients or familiar components, but they're composed in a different way. Like maybe you have rooms that you've seen rooms before, but you've never seen this particular layout of them. And there's that's I think in some sense a deeper form of uncertainty. You kind of have some certainty about what the parts are, but you're not sure how to arrange them. And that might be like involve a more relational or compositional model. Yeah, you do see with hippocampus, you see this really bizarre flickering between states where that seem to be flickering between possible maps of your environment. And so that might be one bit of relevant data on what hippocampus is really doing when its context is uncertain. It's pretty interesting to look at. It's like, I'm in this environment, no, I'm in this environment, I'm in this environment, no, I'm in this environment. And as evidence accumulates, it converges to one.
I just want to add to that. I added a link in the chat to Katja Hoffman and others. They also have a paper called Successor Uncertainties, Exploration on Uncertainty in Temporal Difference Learning, which I think speaks very closely, even the title speaks to your question, Jack.
Thank you.
Yeah. Oh, in additional work in the uncertainty of representation, I shouldn't just quote my own work. Esther Vertes also has a paper on successor uncertainty that's in partially observable environments. Really cool work. It was at Cosine a few years ago, and now it's out. Check it out too.
It was actually just last year, 2019, not Cosine, NeurIPS. I saw it at NeurIPS actually.
Oh yeah, yeah. It was at Cosine in Portugal, whenever that was. And then I think it was it was at NeurIPS as well.
Remember the time we were physically in conferences?
Barely.
All right, thank you so much. I will try to find that paper and put it in the chat too. Okay, Adam, you're next. And as Jack leaves us, Jovo, could you please invite Melanie and or Ella, whoever comes first.
Hi, thanks. Yeah, I was wondering, maybe this is kind of a basic question, but I was wondering if you could expand on the relationship between hierarchy and composition. I think in the slide where you were talking about why we should care, or why you initially cared about hierarchy to begin with, you mentioned things like composition and abstraction, imagination, relations. I think a lot of the times what happens in talks like in this area, because I'm not familiar with like the mathematics behind all these words, I don't know exactly what is meant by something like relations or composition, which seems like very, very, like there are many different types of relations. So I was wondering, hierarchy, I think I more or less understand. I was wondering what the relationship between these concepts are. Thanks.
Yeah, so I think so. Compositionality doesn't. I was talking about applying compositional to in conjunction with hierarchy, and thinking that would lead to a a broader swath of things. But I mean, compositionality really refers to like combining different concepts with some mechanism. There's work that talks about combining concepts programmatically as a form of composition. You could compose things relationally, where like I think the dragon example kind of has that, where it's like you have the nose part of one animal, the ears of one animal, and they have this underlying relation of like how ears and noses and body parts relate to each other, but you're subbing in different parts. So that's the high level topic that I meant by compositionality. It might have a more specific definition. If somebody knows it, they should shout it out, but I don't think it does. I think it does. Oh, go for it, please.
Sorry.
Yeah.
Well, mathematically, composition is a very particular kind of thing. It's a function composition where you operate one function on the other one. And it's closely related to the abstract notion of compositionality that's used frequently in machine learning and AI. And sometimes it is literally a mathematical function composition, but not. So
a composition in math is like, if you compose f and g, then you would take like g of f of x. I didn't realize those were like talking about the same thing. So like if you are, can you express like programmatic and like relational compositions with that kind of notation?
No, I think, so let me just try to clarify. In AI and machine learning, sometimes they mean what you said, and sometimes they mean this other thing. And they're both meaning.
Okay, so yes, sorry, that makes sense. Okay. Yeah, okay. I shouldn't say it doesn't have a mathematical definition, then it does. But yeah, I guess the way I meant it was this more combinatorial way. And then I think, I mean, you could apply this compositional logic to things at different levels of hierarchy. I mean, there's work that thinks about like omniglot digits from Josh Tenenbaum's lab hierarchically or compositionally, where you're arranging like edges, which we would think of as very low level, or you could think about applying compositionality to things we would maybe consider more high level, like these body parts. Yeah, that's what I meant. Relational, when I think you also asked for a more precise definition of relational. Basically, relational refers to a setup where you have entities and associations between entities, basically like pairwise associations, or relations they're also called, but you're not supposed to use a word when you're defining it. The mathematical object most often associated with relational structures is a graph, but you can have relational objects that aren't technically a graph too. A graph just has nodes and edges that join the nodes, and you can also have like multi-graphs where you have multiple types of edges or multiple nodes that are joined with an edge, and you can also have I lost my train of thought. There's things that are talking about pairwise relations of things that go beyond graphs, but graphs are the most common mathematical object. I'll finish my sentence there.
Just want to add.
It's 10 o'clock here.
I just want to add two things, or maybe three things. So first, associative learning is also another approach to thinking about relational concepts. And I recommend, there are a lot of things to read on that in the domain of memory, in the domain of cognition. And another thing that I wanted to say to Jovo, and I think that John Roski wrote a nice thing in the chat. He says, I think composition like functions is different than what people mean by compositionality. And it's actually correct what he's saying. So the notion of compositionality, as you would see in language or as you would see in concept, it's different from that idea. It's much more than the idea of just compositions of functions. And the other thing that I wanted to say was that Adam Shai's question that he asked is a little different from what he had written, I thought, or maybe I misunderstood. I think the thing that he had asked was simply the relationship between composition and hierarchy. And I think that that's an interesting question. And one idea is that once you have the right levels of abstraction, then you could potentially decompose or recompose different solutions in a sort of linear way, instead of having to learn new policies from scratch. Marlos Machado has a wonderful work on eigen options, And he takes deep successor representations. And there is this idea of options, which is an abstraction of policies. And policy is a sequence of actions in order to solve a problem. And options are abstraction of a couple of policies. For instance, just get from here to the door is an option. But the particular trajectory would be a policy. A couple of trajectories could, the particular policy, for instance, get to there and then turn right and then turn left. That's a policy. And the eigen options would be more abstract versions of them. And when you face a problem, and he applied this to Montezuma's Revenge, you could look at the solution as a linear combination of these eigen options, which are these kinds of abstracted parts. So that, I think it's not entirely compositionality yet, but it gets really close, or it gets at least closer. And it's within the framework of successor representation and deep learning. So I think that that's closely related to the question you were asking.
I have a question about relations too. In other words, so when you have sort of like taxonomic relations, or you're trying to bind a scene, which, you know, some patients, for example, get tested and they can no longer relate combine what's happening. So there's a lot of work on sort of taxonomic and semantic relations. Is this the same? I mean, I can't quite see how those are amenable to sort of a graph analysis. Do you think they are? In other words,
I mean, so there was some of the early work with graph neural networks applies to scene understanding. So things like the relation and interaction network, like, are this on top of this? Are these two things next to each other? You know, find the blue thing. Is the blue thing next to the red thing? These are, I think the underlying graph structure where you're formulating your problem as reasoning about ways that things in the scene relate to each other is useful for framing this. And so I think that's kind of how it maps onto a graph. It's an annotated graph, like you want features that describe the nodes, features that describe the edges, and maybe properties of the scene that apply to all of them. In the paper that Jess linked, she mentions, so Jess Hamrick linked a paper, which I also would have been a really succinct answer to your question, which says, talks about definitions of relational and compositional. Yeah, I think in that paper, they talk a bit about relations as they relate to scene understanding.
So just so I understand, well, just so I understand. So in other words, I can sort of understand when you say, is it on top of, beside of, but that feels quite spatial to me. But if you have sort of conventions like, you know, the tallest people go in the back and the shortest people go in the front of a photograph, or you have a family tree where if it's this, it's a son versus a daughter, where it's not really strictly spatial, right? It's conceptual. Is it still going to work? In other words, that kind of relation where you have to sort of get what's happening. It seems to me that it's more than just spatial.
Just a brief note, the example of family tree is indeed the example that the Tolman-Eichenbaum machine paper of James Whittington and Tim Barron solves. So yeah, but go on.
I guess, yeah, I mean, I would think of these types of problems as fundamentally relational, like the sister of somebody, like people, yeah, I guess in the family trees you have relations. In the convention example, yeah, I would also think of that too. I mean, it relates to pairwise relations between things, like, is this person taller than that other person? Maybe you abstract absolute quantities that aren't relational anymore, like this person is in the top percentile of height, so their relationship to many people is that they are taller than them, so I'm not going to compare them in a specific instance. I'll like group them into the category of tall people and then just apply that logic on the person rather than considering the relations. But I would think of those as like, yeah, I mean, fundamentally relational abstractions in some sense. And that like, if you can abstract rules, that's a question of if you can do this type of relational reasoning, because you are reasoning about a relational object. Yeah. Yeah, I might be missing something in the examples. So I'm happy to go on.
No. It was genuinely. I was just wondering as you spoke about how far does something remain relational, right? In other words,
yeah,
is everything ultimately relational? Between the Soviet Union and the former Soviet Union and the United States, and we talk about relations all the time, and I wonder whether everything can fall under that rubric. How far can one push it?
Yeah, I definitely fall in the camp of pushing relational really far. I mean, I think relation is, at least as I understand it, like really fundamental to the way we can think about abstraction in general. Like, what joins all things that are read? They relate to the world in a consistent way when you're applying the filter of color as your relevant criterion. Like what are the what makes an arch different from stairways, to use like a construction example? It's like how states relate to each other as facilitated by the construction element. I probably err on the side of an overly broad understanding of the role of relations. But yeah, I'll stand by it for now.
Everything is right.
It's all relations.
Yeah. You should see the map in her. We should see Kim's map with all the strings between images. No, joking.
I would really like that though.
Right,
yeah, thank you for your question.
So Jova, would you like to invite? So I had people that were prepared to. They expressed that they would be. So I didn't find Miguel. I think he might have dropped off. But Emily said that she would join, and also Salman. So if you could, I'm just gonna put their names in the chat just so that they can also.
Okay. I'm reading Melanie's question.
Okay, now Melanie, please go ahead before we.
Hi. So this question has to do with the role of hierarchy and in learning and creativity. So it seems in the brain, it's not just a thing of static structure, it's also a dynamic that things can be processed in a bottom-up way through the hierarchy and also feedback in a top-down way. Or even just, even start in a top-down way. And that's really important for our learning and our creativity, so on. And the hierarchy that we see in most machine learning models is more of a static structure. It's not this kind of dynamic processing. And I wanted to just get your sense of the role of dynamics and in hierarchy and how important it is to get that into machine learning systems.
Yeah, this is an interesting question. There's a lot in it. I think one of the ways that hierarchy is often talked about in neural networks is, as you say, that how they present in a feed-forward architecture. So if you have like an image classification problem, you take in an image, you spit out an object label, and you would consider the lower layers of processing to be representing low-level information, and the high levels to be high-level information. As the hierarchy is how you go from the raw input to the outputted labels or whatever you're trying to output of your network. That doesn't necessarily have to be the only way that hierarchy is implemented in models. So for example, in hierarchical graph nets, some models are using hierarchy as part of classification. Like you start from a graph with lots of nodes and you're gradually pooling them and then ultimately produce a label. And then some use hierarchy in a closed loop with the reasoning process. So the model that I extremely briefly showed has this quality where you pool and then broadcast, pool and then broadcast. And the high level is continually participating in the low level representation. And there's other models like that too. One model, some of them use different clustering methods, either learned clustering methods or different clustering algorithms from the one we applied. But they do have this quality where the high level is like part of the reasoning process, and there's a back and forth between the high and low level. And I think this is really important because it lets the hierarchy inform the reasoning process, not just kind of be the output at the end of the day, or if you're thinking about gradients, be the input to the gradient learning process. So I think that's part of it. let me read the rest of your question because I forgot the last. I think that, yeah, the first thing I wanted to say is just that hierarchy is not necessarily feed forward in neural networks, although often when people talk about it, it is. And then there was some stuff about visual cortex, feedback connections. Yeah, okay. So I'm stretching out of my comfort zone by speculating on this. But I think another, I think with the forward connections and the backward connections that you do see in a feed forward network, they're doing different things, right? Like feed forward connections there is a sense that you have feedback, which is the how you're propagating the gradients backward through your network. But there's this sense that the feed forward is involved in the prediction process, feedback is involved in learning. And in some of the predictive hierarchical models I've seen of the brain, you have this idea that the forward connections are supplying new evidence and the backward connections are conditioning the incoming evidence based on your priors. So I think that that's definitely different from how they're implemented in feed-forward neural networks and more similar maybe to how they would be implemented in something that has like the high level as part of the reasoning loop.
So just a quick follow-up. So this notion of pooling and broadcast that you have in your model, do you think that's something that happens in the brain, that kind of dynamic, or is it very different, like in hippocampus?
I do think that, I do think that something like that is happening. I mean, at least so pooling is like maybe a specific architectural element for summing together lots of inputs, like you just sum them together, you take the max, or it basically just says you're going to apply some aggregate function over them. Our model of hippocampus, the way I currently think about it at least, is that you have a sparser and less compact representation in hippocampus that can represent the flexibility of the task as you currently understand it. And then you compress that and you sum many states onto one state, or many neurons onto one neuron to have a more compressed representation in entorhinal cortex, and that these exist in a loop and continually inform each other. So yeah, I think that maybe if you think of pooling, maybe it's just like compressing information, is gathering information from many sources and summarizing it with some statistic. I would think something like that's happening.
Thanks so much.
Just a sort of a PS to that question that Melanie asked. Is it? I always thought, correct me if I'm wrong, that when we talk about these compressed representations in entorhinal cortex, I've always been a bit confused, and forgive my ignorance, that I would have imagined that would be where the sparse coding would be. But if I understand it, the sparse coding is in the place cells, and you've got a lot of sort of, it seems that it's not sparse, it's almost like a full network in entorhinal cortex. So is there some, I don't quite, I would have predicted, given what you just said about the compression that occurs in entorhinal cortex, if that's where you'd find the sparse coding. It's always somewhat confused me. Is there a way around that? Because it's the place cells that are sparse, right?
Yeah, I mean, I guess my thinking, I mean, I guess there's a whole lot of cells in entorhinal cortex, and I don't know what the vast majority of, I don't even have ideas about what the vast majority of them are doing. So in some sense, there could be a whole lot of functionality and only some of it's realized. I mean, I think of grid cells as a very compact representation because they have multiple firing fields, whereas a place cell, in theory, only has one, but only has like a small number compared to what grid cells have. So I think at least of the grid cell population as not being particularly sparse, because instead of firing in just like in whatever one field is, you fire in all of your many fields. You might have lower average firing rates, or you might have a large other number of neurons that are diluting the average sparsity. But I'm also curious, I guess I didn't necessarily have priors about whether hippocampus or whether entorhinal cortex would be sparser. So I'm curious, yeah, I guess I might not be addressing the question fully because I'm not sure about the prior that entorhinal cortex should be sparser, but I'm curious where that comes from.
But
Well, I was just
John,
wondering when you said, many neurons onto one, this idea that you could compress it down, it made me think that perhaps that this would be manifest as sparsity, that you just have a few neurons in entorhinal cortex representing a particular compression of many states. That was kind of I was imagining.
I guess I was thinking more you have many states in hippocampus, or many cells in hippocampus that are pooled to a smaller number of neurons in entorhinal cortex. That, for instance, like for every firing field in a grid cell, there would be like a place cell that fires at it. So if you had like 10 grid fields in environment, there'd be 10 place cells that would all map to it to paint an overly cartoonish view.
I see.
Just a shout out to Anna Shapiro's work, Complementary Learning Systems within the hippocampus, the link to which I put in the chat. CA3 and dentate gyrus in the hippocampus have sparse representations, but CA1 actually has these overlapping representations of event that allows for this kind of relational representations that actually fits with the idea of success representation too. So I think it's, in answer to John, I think it's important to note that not all hippocampal cells are quite equal either, right? And also, if you have representations that are in the, especially posterior hippocampus, then you have less sparsity. So they represent more things in the world, or they represent with higher frequency, whether it's a space or something else.
I think also, John, there's sparsity and is kind of meaning different things partially. There's sparsity of the representation itself as compared to sparsity of firing. And you can have neurons that sparsely represent some set of information and fire densely in a given context, or vice versa. So I don't think, I guess we have to just be clear which kind of sparsity we're talking about.
Yes, I mean, I think that's true. I guess I was just thinking, when you finally get to the final layer of a deep neural net and you've just got a few cells that represent cat versus dog, I was just imagining that there was a relationship between the representation and the sparsity of its neural representation.
Oh,
right?
I see. Okay. Yeah. So I think with the with that idea, I guess you have a small number of neurons representing an individual concept, and I guess it just depends how many other neurons are there too. So I guess like I would think of the set of neurons that represent cat as firing pretty densely, but the entire population maybe not firing so densely. So if we think about grid cells, the population of grid cells alone, they're all trying to compactly summarize what's happening in space. So they might be firing densely, but they would, if there was a whole bunch of other neurons too, it would be sparse.
Melanie, did you have something?
Yes, I got.
Oh,
just one thing about that, which is so interesting about this notion of representation is, sometimes I always feel that there is a little bit of a tension between this notion of sparsity and in hippocampus and this huge turn towards constructing subspaces out of huge populations of neurons. Mm-hmm. Right, and sometimes I remember talking to Bruno Olhausen about this. He said, for him there is a little bit of a, when it comes to the notion of representations which are constructed out of huge populations versus the notion of sparsity, where you can converge down onto a few. And I've always wondered whether, wrongly perhaps, that I imagined hippocampus and place cells being more in the sparse flavored world and the grid cells being more like a population, right? And it was almost as though there were sort of two ways to talk about representation. But that might be too Mickey Mouse-ish binary to think that way.
I also want to add to that place fields are not necessarily just one cell, right? So when you have a place field representation, it's not just one cell. So there are actually populations also in the hippocampus that are involved. But go on, Kim. Just wanted to.
I had a fairly tangential comment. Was, what does Mickey Mouse mean in this? You mean cartoonish?
Meaning that I'm being very childish and unsophisticated about.
I've never heard that before. I like it.
But thinking that these slightly different notions of representation, sort of a sparse representation, and then this representation that can only be derived if you actually put all these neurons together in a population. And I was wondering how that sort of collapsed down onto these two different hippocampal populations, you know, in good cells and place cells.
Yeah, I'm not sure. I think I would need to think about it more. I mean, I'm not sure. Yeah, I think with I definitely think hippocampus is very sparse. Sparse does not always mean high dimensional because you know, the population can be summarized more compactly. Yeah, I think I have this sense that that entorhinal cortex is like, you know, more compact and less sparse in some sense. But yeah, I think I would need to think about how it relates to this population view a little more. Thank you.
Emily, and while Emily is here, Joe, the order is Ronan and then Salon.
Cool, awesome. Can you hear me? Awesome, cool. So really nice talk and really inspirational work for me. So my question was about the outputs of this representation and how you think about their role. I guess how I think about it is kind of having at least several different alternatives. Maybe the output is in kind of a perceptual space. Maybe the output is in more like an action space. But what is the output of the hippocampus in this framework? And I don't know, just what are your thoughts on that?
Yeah, that's interesting. So in our model, the output is the successor representation. That's what's like that's what's represented in CA1 according to our model, and then outputted to entorhinal, like deep entorhinal cortex, and transmitted to the brain. That's how we're thinking about it, at least. And things can be associations can be learned to this predictive representation. You have this representation of how much am I going to go to every place. On top of that, you can associate what's going to happen at different states, including what is going to be rewarding. So that's sort of how it basically tries to like summarize what's going to happen next, and then the associations that are learned with different states can be transmitted indirectly via that. So yeah, I think that's how I'm thinking about it, is that this vector is what's being transmitted, the expected number of times you'll visit different states, and that is the like support on which to bound the relevant reward, the thing that you're trying to maximize.
Okay, but how does that influence behavior, I guess, is the question. You know, like if you have the hippocampus with the successor representation, it must either, you know, directly influence behavior or maybe indirectly through some queries influence behavior. How are you thinking of that?
Yeah, so IDA has a good experiment based on this. So basically the idea is that if you're representing predictions about what's going to happen next in this way, you've pre-compiled expectations of what's going to happen next. From each state, you're representing, you're explicitly representing, I'm going to go to this other state some amount, and this other state some different amount. And if you, because of the way this model is implemented, it tends to be easy to change the associations with each state, but harder to relearn which states predict each other. Basically, if you've already pre-compiled which states predict each other and you change that information, you're going to have to relearn a lot about your environment. If you just change the instantaneous associations between what happens in one time step at that state, you can change that and it immediately propagates through the environment. So IDA and colleagues worked on this. IDA and colleagues worked on this experiment where they showed people these sequences and changed either the reward that results after these sequences or the transitions that occur during these sequences. Instead of pursuing along the length of one sequence, you switch at some point, and you're trained on that in an intervening period. And they found that the subjects were faster to learn overall when the reward was changing rather than the transitions changing. So that was one clever way to make a behavioral prediction out of this. You're saying, like, if I'm representing information in this way, then if a change happens, I'm going to need to do this kind of edit to it. One kind of edit should be easy and should lead to quick changes in my behavior. One edit should be more challenging and will lead to slower changes in my behavior. So yeah, that's one prediction. I think basically the set of predictions have this quality in common, that you've pre-compiled. Like, I think the thing I like about this model is it basically says, like, you should cache some statistics about what's going to happen. The model free learning is like, I just cache reward. I just compile how rewarding I think all of these states are going to be in the future. And if pretty much anything changes between behavior and reward, you have to relearn everything. The successor representation is one intermediate point. I'm going to cache representations about what's going to happen next and be flexible to changes in the reward. There's other ways you could carve up the environment as well. Maybe for instance, I'm going to not memorize specifics of what happens down a hallway, but just assume I'm going to go all the way down the hallway and cache statistics about how I will transition down a hallway, but leave open to some model-based reasoning process what I'm going to do at an intersection. There's sort of like these multiple ways you could parse it. And that's, yeah, behavioral condition is about generalizing and how you adapt to change.
Okay.
And Emily, if your question is with regards to which parts of the brain might be involved, we mentioned this briefly in the second paper. I put the links to the paper that Kim mentioned and another paper where we offer a computational idea of this. But briefly, so the hippocampus would have the successor representation, which is the M matrix. Basal ganglia or other regions might have the reward information. And this combination might happen with the facilitation of perhaps the ventromedial prefrontal cortex, perhaps other kind of earlier regions than that. And then there you can have a cascade backwards to motor cortex in order the same way that prefrontal cortex usually when it decides something it cascades backwards in order for an action to actually happen. In a couple of studies during my PhD, I looked at perspective memory using fMRI for the fires. New York City is on fire all the time. You're in the chest, you're hearing it, I don't know, siren. Then what happens is with fMRI, you can look at the representation in the prefrontal cortex that happen along different parts of the brain, even when you're holding another task in mind that you're going to do later. So there is a bunch of different levels of this kind of predictive and prospective representations that are facilitated with the hippocampus and prefrontal cortex. At larger scales, it turns out that PFC damage is more likely to impair your prospective memory behavior than hippocampal damage. And there's some different kinds of information there. So there's a nice literature about this. Very good question you asked with regards to cognitive neuroscience, if I understood your question correctly.
Okay, cool. So it's a lot of distributed kind of outputs kind of thing. Cool. Thanks.
What is happening to John Krakauer, by the way?
The void took him.
Yeah, he has a thing that says that I think his internet is dropping out. He'll come back. Hello, Ronan, please go ahead. And during that time, could you please invite Salman on screen?
Yeah, hi. Yeah, thanks for the invitation. Always really fun these Fridays. It's become a tradition. And yeah, so this is, I guess my question was more related to the beginning of the talk, so sorry if it's kind of taking us back, but you kind of mentioned this idea of the same sort of structures being used for both abstract and the more concrete reasoning, like the physical, like spatial reasoning, as well as like the abstract, more relational stuff. So I was wondering, and when you discussed like the open-endedness, and we're looking for like tasks and where we can sort of apply these things, I was wondering what you thought, like where this meets language, sort of, and semantics, and these like higher level, more abstract tasks, because language obviously has a lot of compositionality and hierarchy, but the question is like, how do we bring like reinforcement learning up there somehow, or like where do you think it meets? Like a lot of people in NLP, where I'm more coming from, they are like not interested. I mean, not interested, but like reinforcement learning is seen as sort of this, yeah, like not, it's hard to optimize and complicates things, and maybe we don't need it, and maybe we can just do GPT-3 and all that.
Yeah, language is hard. So I don't want to do a quote on this, but yeah, so I mean, yeah, so one thing that's...
Do you want to mute yourself? Like there's a sound of pots and things. Thank you. Go on.
One thing that, yeah, I mean, language is is really complicated. I think one thing that's really different about the tasks where like a task you give an animal and a task you give humans is that you can communicate with language what the task is with a human. I mean, every task that a human is doing, even if you have an animal translation of it, it will have this property that the animal learned this through like a brutal trial and error process, and humans rarely do. I think in the specific example of the morphing birds experiment, I know they showed lots of examples of morphing birds, and I know they made an effort at least to be agnostic in the language, that they had to extract this from their experience, and they had a long pre-training period. So that might be more analogous to the learning problems. But I mean, yeah, as John mentioned too, like one thing that's going to be really different about the way animals and humans generalize is that humans can like operate over these abstractions that they acquire instantaneously from language. And maybe they refer to an element of experience and still have this relationship to something that happened more gradually. But the process by which they're imparted is a lot more abstract. Language also has a lot of compositionality. So there's theories that like maybe the compositionality of language is generalized across different reasoning processes humans do too. I haven't worked that much in an NLP. I've honestly always been a little bit scared of it because it seems really hard in a lot of ways. Like I think on the one hand, it has a lot of this like hierarchical structure that's really interesting. Like these ideas about grammars and compositionality were largely like developed on language problems. But yeah, I mean, there's also so much data and regularity of the local structure that a lot of models that aren't necessarily trained to infer hierarchy or for abstraction or be like explicitly compositional can still do a pretty good job predicting what's going to happen next over a reasonable time scale because we have written a lot of things down, at least the way that I think about it. So yeah, I mean, like GPT-3 is really, really amazing. I mean, it does, its autocompletes are really impressive. And sometimes it makes mistakes and sometimes it does like a really interesting job. But it's probably not doing something like hierarchical and abstract because that's not really put in there. It's just sort of aggregated over the big set of data.
I also want to mention there is quite a bit of NLP and RL in work that combines them. I put the link to one of my colleagues who is a manager of the whole groups of people who work on this. And I think James McClellan's paper recently, the review that they had also is very related, where they suggest that some of the next steps, and I will put the link in the chat, some of the next steps for NLP models would be to have some kind of a correspondence between representations learned in the neural network and the NLP components. So that is something that things like GPT-3 are entirely lacking. They don't have a representation of the world that's devoid of the parrot-like word embeddings that they're using. It's not grounded in a representation that interacts with the world, really. It's just wrapping up the outcome of other agents who are grounded in the world and then using that. That's why people call it like a parrot thing, right? And so I think that it would be the combination of representational learning and NLP and the ways to link them are very interesting directions. There is text world, there is ALF world and ALFie. There is a couple of things Alfred. Like there's a bunch of things that Microsoft research folks have done that are related in this domain, and I think there's a lot of cool other stuff to come by. I think it's a very interesting area you mentioned.
Do you think it would be like essential then? So like the sort of reinforcement learning style as some kind of maybe pre-training or even like training it alongside, like this is what I'm kind of understanding from you, Ida, that you'd say that you kind of need it. You can't get away from sort of needing it, because I often have this discussion like, why do we, like, it's so expensive, it's so hard, why can't we just do everything from text?
No, that's a great question. So first of all, if there's an engineering problem somebody wants to solve, they might say, hey, it's enough for me to just use GPT-3. And some people might say, hey, have you seen how much nonsense it generates? You might need to at least add a controller module to the system who reasons and just monitors so that it doesn't spit out nonsense sometimes. But more specifically than that, some of us are interested in models that are either human-like or biologically plausible or have something to do with brains. And brains, language is just one of the ways, or natural language at least, and not all species have it. There are other different kinds of simpler notions of language that other species might have as well. Or there are other kinds of non-verbal, non-natural language that humans use. And as the work of Stan DeHaan and others have shown, whether it's in geometry or music and other domains. And it seems like it's a very interesting domain, but it needs to be grounded in something else. It is names that we have given to abstraction of representations that the agent has learned in interaction with the world. And it's grounded in what you have learned about and generalized and abstracted about the world. And that's the part that's the important part that any kind of representation learning, for instance, the reinforcement learning framework can help to provide. So you need like a representation learning component where the language is grounded and some kind of a reasoning component. The advantage it can have for RL is, so if I want to reason about, for instance, what John was describing earlier, it's a V-shaped corridor, I probably need to go to the left arm or something. It's not too hard to imagine doing that if you have a combination of RL plus the NLP component, where it sees the structure, it knows that at a certain level of granularity, a certain level of abstraction, it has an association for that structure with some word. You might have like an analogical reasoning component here or not, but that's also something that there is neural networks for it. And then it can start to make inferences or ask questions about what to do in the language domain, translate it to the representations that are going to go backwards to translate to the actions, which is not very unlike the cascade that happens from anterior to posterior in the prefrontal cortex once you come up with something. So the language might help with the reasoning, and then the decision can cascade back to motor responses, for instance, or actual actions. So one thing that we are actually working on is related to this. Can we have an agent that has both kinds of things and can ask itself questions in order to explore more efficiently, right? There are many different ways to do these kinds of things. We are actually looking for an intern. So if anybody's a grad student and wants to do an internship, that's it's a very interesting area, I think. And I do think that both NLP will need it because of all the mess that we are seeing it's doing. And I can link to some very sort of disturbing articles. For instance, GPT-3 is very, it provides very violent imagery when the word Muslim is involved or when there is a woman with a hijab in a photograph. And there is a wonderful Medium post about it. It's called I am suddenly covered in blood or something. It's just this horrific thing. They asked GPT-3 to complete a sentence. And it starts with, oh, I'm wearing my hijab or whatever. And it leads into this extreme violent imagery.
I found this too once. I entered like something like you were a jerk or something. And I got something like wildly racist. Like it was really striking. I mean, but it's trained on a swath of data of which there apparently exist ugly corners.
But why
exactly. Let me make the point, John, first. Let me make the point.
By that.
Let me make the point first.
I don't think it's surprising.
That point is not the issue of surprise. The point is, why would NLP need some kind of a representation learning or reasoning module to be added to it? So it's not just the parrot. And the point is, one of the advantages that even the NLP engineering, I'm very inclined to say bros, but I shouldn't. Even the people who don't care at all about brains, they don't care about like reasoning, they don't care about any of that. Even them would be interested in this because they need to figure out some kind of a module that can process what's coming out of the GPT-3. Part of the reason is, and in that article you can see, you can't find all the possible horrific cases and then fix them by hand. That's just like a very difficult job. It's trained on so much data, and you don't even know what kind of data it's been trained on. So it's very hard to do it on the data side with a data science approach. However, if we imitate the reasoning, controlled reasoning that humans use when we don't say everything that comes to our mind. Because there is a kind of a control cognitive process going on. At least the least we can offer to these models is to give them some kind of a ability to process, does this make sense? Like, what are the social consequences of this or whatnot? And then monitor it. So even for NLP people who only want to do engineering things, I think that this could be helpful.
I can add also, just out of, you mentioned internship, so in the industry, I know that they're not using these models. They're scared of using them. Like IBM cannot sell, the conversation agent technology because people are scared. Like, what is this thing going to tell my customers? And it's like, I think for real across a bunch of companies.
Yeah, so this is actually a thing that's like a big topic on the neuroscience team at DeepMind. Like, I think I work more on the realm of humans and animals are good at stuff. Let's get machines to be good at it too. And another aspect of it is like machine learning algorithms are largely uninterpretable. Like they've got a big sloppy mess of computation going on, and we don't really know what it's going to do. We can't predict that it will stay in the range of acceptable language, and we can't necessarily like relate its decisions to things we know about the world. So I think an analogy has been made to this problem of like the brain is also a black box. We don't know what it's doing, and some neuroscientific methods might be useful for trying to pick that apart, just as we like try to pick that apart in neuroscience too. I'll also say there's a bunch of work actually from DeepMind on people who work on concept stuff, and therefore, as Ida was talking about, grounded language. And a lot of this work relates to like answering questions about scenes. Some of it relates to this clever data set. They also published a variant that's called not so clever, which is a simplified version of the problem. Irina Higgins has a paper on a model called SCAN that relates learning of abstractions to like language description of things. But yeah, I mean, there's some things on like question answering about scenes that has this like multimodal component that makes it grounded, and also like has this relationship to abstraction too once you start trying to ground them. Yeah, it's a good problem.
Thank you.
Jova, did you invite Salman or Jonathan Flowers? They were the next invitees. And while you're inviting them, maybe I can read Miguel's question. Miguel asks,
Thank you.
Hi, dear Kim. This is perhaps out of context, but I have the feeling that I have learned most of the neural part, how hippocampus works, and most of the MLAI part, RL, eigen decomposition, etc., separated, and I find sometimes hard to relate them thoughtfully to answer questions in both fields. What would be your recommendation? Which functional papers, tutorials, etc.? That's Miguel Munoz.
Hi. Okay, wait, so sorry, I clicked a button.
Could you also invite Salman, please?
I'm working on it.
Oh, thank you.
Yeah, so yeah, I guess the simplest answer, this is a big problem, right? This is the problem of like how to pick a research question. I think the easiest answer would be try to answer one at a time rather than answering both questions at once. I mean, I think like you can ask good neuroscience questions that are like, we don't know how this part of the brain works, but we have some machine learning tools that might be relevant to it, or mathematical, theoretical tools that might be relevant, or we don't know how to do this machine learning thing. Do we know anything about how the brain solves this problem? Sometimes the answer will be no. Like, I mean, there might just be some problems you're working on that like we don't know how the brain solves them. That's probably most questions to some extent. But yeah, I mean, I think one thing that's interesting about working on the neuroscience team and having like this neuro entry into machine learning is there are a lot of problems that are unique to either field. There's some questions that we want to know about how the brain works that we don't necessarily have a current theory about how we'll relate to a machine learning problem. Some examples of these are often like biological or what's called like low-level things about how ion channels work or how dendritic computation works. And that's a little unfair because if we learn something like we could learn something new about that will relate a constraint that is interesting to and important for machine learning problems specifically. But in general, there's a lot of things people work on that are like important to know how the brain works. We don't have a theory about how to relate it to machine learning. And there's also like machine learning problems that are basically like, how do we get this to work more efficiently over tensor processing units, or how can we solve this particular benchmark task that isn't really something humans are particularly good at, or something that humans seem to do in a different way. And then there's problems at the intersection that is maybe like a shrinking category, but like one of them is how can we get flexible behavior transfer, structured representations, grounded representations. There's like these things that we're both not sure how humans and animals do them. We're also not sure how to get machines to do them well. and staying in that zone, I think, maximizes the probability of finding something that will be useful to both fields, if that's specifically a constraint you're interested in. But I think there's probably a lot of trial and error, and maybe like staying in this area and thinking about both fields will allow you to like close the loop and have insights that are relevant and from one field and translate it to the other. But it's definitely not a guarantee, because you just can't predict when you're going to have an insight about something. I think like fundamentally that's really hard to do. One paper that immediately comes to mind, because it was written by my advisor, is this paper on neuroscience AI, written by Matt Botvinnik and some other people at DeepMind. And they talk about this idea that there is a virtuous cycle between neuroscience and machine learning, that there are problems that are open in both neuroscience and machine learning. We don't know how to get machines to do them. We don't know how animals do them. Framing in machine learning terms how neuroscientific processes work will mean that the things we learn about them can be ported over to give good ideas for machine learning, and vice versa. Ideas we have in machine learning can use to describe processes in the brain in a normative framework that could be useful. So I'd recommend that paper. I'm sure there's a lot of papers where people use machine learning techniques to analyze data. There's a lot of papers in reinforcement learning where ideas that are really developed in like both machine learning and psychology have been used to describe the brain. Computer vision also has had a lot of like deep learning analogies in particular that have been applied to it, like Yemen's and DiCarlo is a classic there. Do you other people whose faces are showing have other papers to add to the pile?
I think that was pretty great, honestly. And your tutorial with Tim Behrens.
Oh, yeah.
Your own video tutorial.
My own tutorial.
Let me advertise you. No, go on.
So Tim Behrens and I worked on a tutorial for CCN some number of years ago, either a small or large number, I can't remember anymore. But we talk, it's called Representing States and Spaces. You can find it on YouTube. We talk a lot about ideas in representation learning and reinforcement learning and how we think about relating them to the brain.
Just one thing before Jonathan, you know, it's interesting that when John Langford, I've seen him speak twice now, so Ida, forgive me if I mix up where it was, but he has this wonderful thing where he goes from a worm to a spider to a wolf, and I think after that it's humans, right? And at the moment, most sophisticated RL is at the level of spiders, right? And, you know, of course, we had Tony Vader on, who feels like DeepMind should try and be a mouse first before it becomes a human.
Mm-hmm.
I was just wondering whether, to the question you were asked, do you agree sort of with the point that John's making, which maybe you could argue is even below the mouse, that the best point of fusion of neuroscience and machine learning is going to be in the behaviors, as you said, sort of flexibility, transfer learning, some generalization, is going to be at the level of animal behavior rather than human behavior? I mean, of course, everyone's super impressed by the ability to beat, you know, Lee Sedol at Go and these human-like benchmarks. But I find it kind of interesting that there's a little bit of two conversations going on here. One is, in terms of at least RL, it's spiders and mice, yet we have these human benchmarks. But it sounds to me like you're saying the most fruitful overlap of neuroscience and machine learning will be in some of these animal behaviors rather than human-specific ones. Is that fair, or can we have our cake and eat it?
Yeah, it's I guess it's a hard question in some sense. So I mean, I think one of the I guess with neuroscience, there's this trade-off of like what you can look at, neurally speaking. So I think a lot of questions about cognition are really hard to ask of anything that's not a human, like language questions. And I mean, in some sense, like, you know, we're talking about how some of the ways that like GPT-3 is like a parrot in maybe some senses. but it's like a really, if so, I mean, it's a really good one. It shows you how far that approach can get with capturing something that feels kind of like language to us. So I guess like, so some things like we need to, animals can't be as good as GPT-3 by some metrics, except maybe parrots. But for that kind of stuff, we would probably need to look at humans, and the neuroscientific tools available to us would be a little more limited with animals that do really sophisticated behavior, but maybe don't particularly have this quality of flexibility that we think is really important to cognition, like flies and spiders. Like flies and spiders and insects can do amazing things. They're incredibly specialized. They're, like they're much better adapted to their environment than a human would be. But since we're interested in this specific quality of intelligence that characterizes human intelligence, they would have less relevant stuff to say about it maybe, but we could ask more specific questions of the circuitry. So if we're looking for specifically neuroscientific inspiration, I think one of the reasons I'm kind of framing things in terms of animals is because I think it's, the methods make it a little bit easier to unpack the algorithm. Although, like, of course, there's options at every level. I think that's a big part of it. In some sense too, this spectrum of animals. I've heard people talk about that at DeepMind too. This idea of X level AI, where X is an animal that we think of as some amount smart, and it's a little bit hard to make. I think one of the things about it is just it's hard to compare intelligence among animals to at least in a way that then ends up being actionable for making an algorithm. Because mice and rodents are really good at navigation, probably better in a lot of ways than we are. If we're interested specifically in AI that has the quality of intelligence that it's flexible, transfers well, generalizable, abstractions, interpretable, etc., we might not need to be nearly as good at all the stuff a mouse does. We don't need to contain a mouse. Humans don't contain a mouse. So it's sort of we want to maybe go towards it, but then veer away before we overfit to any particular animal.
So Kim, I know it's very late there, but we're very happy to have Jonathan Flowers. He's our resident philosopher of the Salon. I think one of the few pragmatists on Twitter that I know. Probably there are many others, but he's the only one that I know. So looking forward to your question, Jonathan.
I actually don't. Well, actually, I was going to say I don't have a question, but now I do have a question. Why are animals and humans worthy of being used as benchmarks in the first place, which again is the philosophical question? Because if you want a machine to accomplish a task in a particular way, you probably want to train the machine to execute that task in a variety of contexts so that it can take up what it has, and I'm going to use the word learned broadly, what it has learned from engaging in that task in a whole bunch of different environments and then apply it to a novel situation. So your example of the spider, right? If we wanted a complex intelligence to navigate a unstable terrain, a spider might be a good choice, right? You would embody the, say, intelligence in a spider-like form and thus turn it loose on a complex terrain and learn something about how, say, or said organism navigates the world. So my fundamental thing with GPT-3 and the rest of these things is, one, we're using these benchmarks outside of the environmental contexts in which they developed, right? So GPT-3 is a parrot because it doesn't need to talk to people, right? Unless you're training GPT-3 to hold conversations, right? Or to engage in rap battles or poetic duels, so on and so forth. It would have to understand the conditions of language within that specific context in order to do it well. And then it could, presumably, if you got it advanced enough, export what it learned there and apply it to similar situations across the domain of its experience. But from my understanding, nobody's trying to get a machine to do that. We're not training it within a specified context to accomplish a task to make it happen. So this gets me back to my question. And it's a question that I pose kind of infrequently because, it gets me into fights. why are humans and animals good benchmarks in the first place? What do we want these artificial organisms to be doing such that a human or an animal is a good benchmark? And if whatever it is we want them to do has nothing to do with being a human or an animal, then we might want to rethink our entire, say, benchmarking process.
Yeah, so I think the main problem is that the thing that we, like using we kind of broadly, want to do is make machines that are intelligent. And that is a really ungrounded problem. Like if we want a machine, I think this other topic is called like narrow AI, right? Like if we want a machine to be really good at X, we could maybe look at a particular animal that's good at X, like the spider in the rough terrain, as our inspiration and try and recapitulate its advantages as much as possible. And if we, for any given specific task we want, we could try and make something that really like uses learning to fit itself to the specific contours of that problem and what it requires. And you might use animals as a benchmark to say, look how good a job we did. We did it better than the animal that does this best. And that's sort of like a reference frame we have for whether or not to be impressed. Like this is, with Go, that was the same thing. It's like, well, we did it better than all humans. Like, well, are humans good at it? Like, I don't know. It seems hard. Like, I can't do as well as the best human, and this machine is better at it than me. But machines also are like terrible at a lot of other things that all humans do well. Like, flexible things. So I think in some sense, when you know what you want to do, you should just do it. And the role that biological intelligence or high performance can play is it might give you more ideas for how to do it. It might give you inspiration that is useful and beyond what introspection gives you. With the goal of making AI that is intelligent, I think one of the big things we lean on with biological examples is that we don't really know what we mean by intelligent. We just know that humans are it and animals seem to be kind of it. So humans can be a good reference for trying to make something that feels like it's intelligent to us. And we think that will be bootstrappable and lead to something kind of cool and impressive. That will be like maybe an all-purpose solution to problems we haven't thought of yet, that it'll have this like open-endedness to it. So I mean, I think that's a big role that it serves with the specific goal of AGI. The problem, and I think a very fair criticism of AGI is that like, if we don't really know what we want to do, why is it a big deal to try and solve it? Yeah.
I just want to read out John Roski's comment. He says, is it problematic to design an artificial heart by emulating the properties of a human heart that let it do what it does?
Wait, sorry, can you read it again?
I think he's using an analogy here. He says, is it problematic to design an artificial heart by emulating the properties of a human heart that let it do what it does? So I guess he means, in an analogy, if you want to design a particular thing, so it seems like a engineering analogy. If there is a particular thing you want to design, and you could emulate the properties of that thing in another species, and if that's in humans, that's helpful. But to John Flower's question, I just want to add that we are actually actively doing research on showing that some of these things that pass benchmarks, if you observe their behavior, it doesn't look human-like. So we just ran a Turing test where we showed videos of an agent playing a game and humans playing a game, and asked participants to say which one they think is more human-like. And to be clear, people were not at 100%. I was shocked. I thought everyone could tell who is human, and because the algorithms weren't like, one of them was state of the art, but it wasn't the best possible imaginable algorithm. But about across two studies, about 75 to 83% could tell which one is human, or the human judges pass the Turing test at least. And then we are training classifiers that are going to do the judging. And that's part of the reason that we are excited about this work, because we are designing some classifier to be able to tell what's more human-like behavior. And so in the process, it can understand that, hey, I'm solving this benchmark, but it's not human-like the way I'm solving it. So yeah, so I think that there are interesting future directions where we want to see, where do we care though? So we care about it because this is navigation behavior in a game. You want your AI sidekick to be able to navigate in a way that's believable. But some engineering person, or the example of John Rusky was interesting partly because of that, because first of all, you don't need to know how a heart really works in order to make it engineering-wise work, the engineered version of it work in somebody necessarily. You don't need to know everything about the human heart. And secondly, you might say, I don't care that it looks exactly like a human heart. I just care that it serves a particular function, right? Mm-hmm. So two things. There's the engineering people who can tell us, I just don't care about human likeness or biological plausibility. And there is us who say, hey, we do care, and now let's come up with methods to assess the human likeness and not stop at benchmarks, because a lot of things can solve the benchmark or reach the benchmark, but they might not look human-like.
There are two things, yeah, I agree. I think there are two things being confused here. You know, the heart example is a very interesting one, right? Because when people try to make artificial hearts, they indeed did try and abstract and idealize from how the heart works mechanistically, right? But if you go into heart surgery and go on a heart lung machine on a bypass, right, that doesn't look like a heart, right? So in other words, you can get what you want done, and you can do it mechanistically in quite distinct ways, right? That's the point I think was very interesting, Kimberly said about you're not playing Go very well. Is one of the things I think we can safely say is that the way most people play Go and the way that the machine plays it is quite distinct. Similarly, you know, the other thing about benchmarks, to sort of Jonathan's point, is, you know, the furthest that a human can dive without scuba gear is about 60 feet, right? If you go in a submarine or something like it, you can go to 35,000 feet, right? Now, there's absolutely no relationship whatsoever about how the human got to 35,000 feet versus how they got to 60 feet. So I think you have to decide whether you want to meet a benchmark where you can have a complete disjunction between how it's achieved, or do you want to actually, as Ida says, get to 60 feet the way a human gets to 60 feet, or are you happy being a submarine getting to 35,000 feet? So I find people get this, and the last point about benchmarks is it sort of gets to the way that movies work, which is, it seems that the assumption in all drama is that you get to the essence of human psychology when they're under extremis, that there is no interesting stuff about humans when they're having ordinary, boring lives. They have to be under extremis. And I feel sometimes that benchmarks like Go are the extremis argument. Can we push a human to the very limit of what they're comfortable doing? And that tells us what humans are capable of doing cognitively, when actually just going to the fridge and getting out a Coke is probably more interesting than anything to do with what happens during Go. And so I think it's really, you see, so I think we have to be very careful about mechanistic versus non-mechanistic emulation, and also not making the mistake that the system under extremis is actually the best place to look for the general principles.
Yeah, there's this concept called Moravec's paradox, which I learned about like fairly recently. This idea that like the things that are harder for humans are maybe not as hard for machines, and the things that are easier for humans seem to be harder to get machines to do. Like symbolic logic, for instance, feels a lot harder than recognizing a face, you know, applying consequences and thinking them through. But it was a lot easier to get machines to apply like simple symbolic propositional logic than it was to get machines that could do like good object recognition and facial recognition. And part of that theory is that like the stuff that comes more intuitively to us is a little bit harder to articulate. So maybe there's some element where like we are just not even good at recognizing how hard things are, and also we just like have more specialized machinery for it, or it's a very like, you know, distributed and inarticulable process. I think, yeah, so I mean, I do really agree that this idea, it ends up being really like kind of hard, especially if the thing you're trying to infer is your model intelligent, is the machine learning algorithm you made doing a good job at something. It's hard to know whether or not that's the case without having some idea of like whether or not the task is hard. So one kind of like somewhat easy way to impress people is like, well, humans find it hard. But that doesn't necessarily mean, as you're saying, that it's like central to human cognition, or it's like really central to the intelligent processes we want to capture. So yeah, I mean, I do really broadly agree that like studying normal humans is maybe better. I mean, it reminded me too of this article by The Onion I saw a long time ago, which the title was "Dolphins Not So Smart on Land." This idea that they didn't pass a battery of cognitive assessments when they were taken out of water. I'm not sure like it has a deep conceptual connection, but that is what I thought of. Yeah, I mean, the last thing, like I've probably heard like 80 different accounts of like how Orville and Wright finally figured out the airplane, but like I've heard both people argue they didn't figure it out until they stopped looking at biology and started thinking about flying. I've also heard they figured it out because they found the right level of abstraction at which to translate bird principles to plane principles, that it was in a matter of like finding the relevant abstraction. I don't know which one.
That's exactly
Yeah.
the heart-lung machine versus the mechanical heart. Exactly right.
Yeah, yeah.
When are you trying to sort of get mechanistic abstraction, and when are you trying to get function abstraction? And it can easily be that they get conflated. It's that's exactly right. Yeah.
Yeah, I think so too. There's like a functional level of abstraction you want to isolate, and then that is the level you want to use for inspiration. And I do think, I didn't parse the question right away, but this idea of like, is it problematic to just like copy a human heart for an artificial function? Like maybe it is, because you maybe know that it does the pumping thing, but you don't know what else hearts are supposed to do. Maybe they will turn out to be irrelevant. Maybe they're supposed to fail when you're 200 years old or something for some reason we've never found. Like, so, you know, it would be risky without knowing the array of things that it is necessarily optimized for and what it's good at to just like copy it directly. But getting ideas that are well understood. And I think that also is like a role for theory and math. I think machine learning is a very empirical discipline, and so is neuroscience. And this like conceptual abstraction is really not either of them, but a necessary part of responsible translation.
So
I wanted to invite Michelle to ask this question, but go on, please. Continue.
Yeah, sorry. Yeah, the dolphin example is actually, I mean, you laugh at it, but it's actually pretty good. Dolphin's not so smart when taken out of water. A dolphin is not so smart when taken out of the context in which the organism emerged and with which it transacts, right? Mm-hmm. So to expect a machine that does not have a human embodiment to do the human thing super well, right? As much as I like to, you know, hate on Mark Johnson for his abuse of pragmatism, there is something there about the ways that we abstract away from our bodies in particular modes of reasoning. So to expect a machine to perform human-like tasks without a human-like context is to ignore a whole chunk of our, you know, experiential context that gives rise to the ways we even make relations and then take those relations and apply them in novel situations. So I mean, yeah, that's generally my broader position. I might have to find that Onion thing.
I could link it. Ida's been sending all these papers, and my contribution to the thread will be this Onion article. But yeah, I'm glad you appreciated the depth of the analogy.
Right.
I want to add, Jonathan, just to your comment. Sorry, before getting to Montreal, that machines are already better than humans in everything else in lots of learning tasks, right? So you try to solve linear regression. I guarantee you the machine has a higher precision answer than you once there's more than like 8 data points. Or another really good example, I posted a link. There's an article from the 90s of learning with an unreliable teacher. So if you take the world's 5 best people at whatever task, say radiologists, they'll all be somewhat errorful. But if they're unbiased teachers and you train the machine learner on all of them, the machine learner will average out their errors and be better than any of them. So you can easily train the machine to be better than
until you ask the
any
machine
particular
to know what to tell the patient.
Yeah, once you get past the diagnostic task, you start getting problems, right? So I have to go through complicated processes of inquiry to diagnose what's wrong with my motorcycle. Like right now, it's too cold, and I probably should test the battery later. But if I hooked it up to a machine could figure out what's wrong with my bike much faster. So what you're talking about is the speed whereby a given organism runs through processes of inquiry to come up with to make a indeterminate situation determinate. A machine probably could not reliably, no matter what popular culture says, resolve the determinate situation of a boxing match for victory faster than a human could, because there's a lot of other contexts that go into it, right? And so I take your point that machines might be better at some tasks than humans do. And I want to note that the tasks you're describing are all diagnostic tasks, right? As opposed to how do I get around this problem, or how do I resolve a ongoing indeterminate situation, which machines are getting better at, but only within defined contexts, Go, chess, so on and so forth, right? So this, I take your point, but I also want to return your point to the fact that that is extremely contextual and limited to a specific set of tasks, and is reliably grounded in the speed at which a human versus a machine can run through the processes of inquiry to complete the task, right? I don't think a machine could beat me at boxing.
A wall can beat you at boxing.
Yeah, I'll take your.
My dad got.
Yeah.
No violence, no violence. We can have a beatboxing
My
match.
dad broke his hand trying to punch a brick when he was younger, so I guess that he really did get beat by a wall.
Actually,
I would definitely look at a boxing match, but a slapping match, who knows?
wait a second. Kim actually has 2 black belts in karate, so I think she's gonna kick any of us.
So I can beat a wall. That's what that means.
Yesterday, I think poor Montreal's been sitting there in the lower
Yeah.
right-hand corner.
Yeah.
And I'm gonna leave
Can I say one more thing though? It's just a little quick thing. There actually is a Twilight Zone episode specifically about a machines boxing, which I recommend. And actually, like, the very point it's making is that humans will get beaten up by machines, because I mean, they are presumably can be a lot stronger, and if they're sophisticated enough to punch quickly, then they could be like really good at stuff.
All right, Montreal.
All right. So, I mean, I'm not clear if I should comment on that, because I actually have concerns about that as well, or the animal thing. But because this is about AI and learning, so I was having a conversation about the Go robot, and the idea was that it's a really sophisticated system that recreated essentially the architecture, and then they ran it and it learned, and then it had the proper outcome of being really good at Go. And my question, right, is that if we're interested in learning and the general, I guess, cognitive medium that's responsible for learning, is it safe to say that we recreated it when we set up the architecture in AI machinery, or is that not even the interest? Is it just sort of getting the effect and then making some interpretations, post hoc?
It's an interesting question. I mean, at some level, actually, would you mind muting yourself again, because there's a bit of a feedback. Thanks. Sorry. So I would say it's not quite capturing the process, because presumably the machinery that allows humans to be good at Go is not unique to the task of Go. So there is probably like the processes involved are more general purpose. You can use memory for Go, you can use it for lots of other stuff. You can use planning for Go, you can use it for lots of other stuff. So the fact that you get the same inputs and produce the same outputs doesn't necessarily mean that it contains the same cognitive process, because that cognitive process seems to be structured in a way that produces all these other things too. You could also ask, like, if you just had 2 neural networks that were trained to play Go, and both were very good at Go, or maybe even produce the same behavior, it's not necessarily, at least like on the tasks you saw, it's not necessarily the case that that one contains the other, that they're doing exactly the same thing, because there is this, like, I think there's this whole space available for how they could be computing it. Different algorithms might lead to the same behavior on the set of things you check. I think if you looked at like maybe all possible inputs and all possible outputs, you might be able to conclude they're doing the same thing, but there's probably examples of that not happening. Yeah, Ida, do you want to?
Yeah, I just want to say that the question that you're asking is, I think, important. And there is a paper by Siddhartha Sen, one of my colleagues, and other colleagues of his. It's a collaboration between Toronto University, Cornell, and Microsoft Research. They try to assess the human likeness of the chess plays that had happened. So they looked at the huge database of the moves that humans make, the way that humans make moves, and the moves that superhuman chess players make, and then they try to align that. So, and this is something that we have discussions around what would be the future of this, because we wouldn't just. So even the Go player, what if it wanted to tell a human what it's doing? Like, would it be able to do that? Does it have other kinds of ways of engaging with the idea of how it's playing? In another work, we are looking at grounded learning, and how you need to ground the sort of reward, meaning, signals, interactions in some kind of a language game where you can do a back and forth with another agent or with an environment. And I think that these are important aspects that the future of superhuman or human-like game engines need to have. I added the paper there in the chat. I think there are other papers that I'm definitely missing, that like other Maya versions, which are human-like chess and things like that. And I think it's important to see, when would the machine solve chess or Go or these things like humans? When does it show human-like moves, and when does it actually use representations that are human-like, which goes back to John's earlier, John Krakauer's earlier point, which is about difference between sort of emulating behavior or emulating the actual underlying mechanism. It seems like in the case of the way that the Go or chess is solved by these superhuman engines, it's neither. It's neither making human-like moves, nor does it solve it the way humans do.
Yeah, no, I think I agree with that. I was just more or less, because I'm more or less a novice to the machine learning field, and I know that's a general interest in it to study intelligence, and I'm assuming we think intelligence is some sort of universal that can be captured, and we're just wondering how you would, study that using this sort of machine.
Yeah, I think that paper is an example of how, but it's a bigger question, what you're asking.
I mean, just a final point, to I think what Kim was saying about intelligence in general, right? I mean, would it be fair to say at the end of the evening, and I have a Manhattan here, so I'll blame it, sweeping statements that that in a way you want to find ways to identify structure in the world, right? You want to model the world, and that intelligence, it seems to me that there are many ways to structure a game. There's structure in Go, there's structure in chess, there's structure in the world, there's structure in a maze. So do you think it matters whether you have the same mechanism for the discovery of structure, or that you just call it intelligence if you have a variety of ways to discover structure and then, plan on the basis of that structure? Do you think that might be the closest to what neuroscience and animal people and human people and machine people are doing, which is the discovery of structure through learning so that you can then plan on it? Is that what we're all after? And sometimes they converge, and other times they're just doing it in qualitatively different ways, but it's all about structure that you can plan with.
I think that is, yeah, I mean, I think that is a really core unifying principle. I mean, and it's not, I don't think it's like overly strong even, or overly controversial to be like, because structure is such a broad concept in of itself. But yeah, I mean, I think a lot of the reasons people want AGI and a lot of the things that like descriptions of intelligent behavior have in common is this concept of like understanding and something so deeply that you can plan about it effectively and reason about new implications of this understanding you have, like come up with new ideas that will work, or come up with new ideas by thinking about the structure. So yeah, I mean, I think that's a pretty deep concept to coming up with to like what we want in intelligence. I think you also had a bit about like if there's if it needs to be like the same structure defining finding mechanism, or if lots of structure finding mechanisms will all be blended together. Yeah, I think in some sense, I guess depending on how much you zoom out, many processes that are interacting would be one process in some sense. But I'm not sure I have a super strong opinion. I think I would find it very satisfying if there was one structure learning algorithm to rule them all. But you know, also no free lunch, so who knows? Yeah, go for it.
I just want. Were you done?
Yeah.
Okay, sorry, I didn't mean to interrupt. But John, I think the structure is a bit too vague. I think I want to refer back to some of the things that Neurokim was saying earlier, which is it's structure. Sorry, just threw that in there to see what happens.
I love it.
Okay.
She's not a rapper. You can call her by your first name.
I could be a rapper. You don't know everything about me.
I actually do know about you.
Well, regardless,
so you'd
I think
called RL Kim instead of Little Kim.
Going with Neurokim.
Actually, that's pretty good. Okay. Now she has to become a rapper, but go on.
So, John, like eigenvectors are structure, right? It's not just structure. It's structure specifically that the agent can use to perform the behaviors that they want. And so a dolphin may want to find a different structure than a human, and a machine may want to find a different structure for representing Go than a human, because they have different computational constraints and resources and capabilities. So it's not, I don't think there's going to be a universal structure learning algorithm, as Kim said, because there's going to be different agents with different capabilities, and they want to find different structures.
Yeah, I think that's a really good point. I mean, the structure you find is conditional on like the body you have, the perception you have, and then also the computational algorithms you can apply to it. If you find searching really deep trees super easy, you should have a much different representation than if you if you have lots of capacity for memory but very little capacity for implementing operations over time. So yeah, I mean, I think if I to defend the one true structure idea, I mean, I think you could represent these in a common space where you're viewing their trade-offs as lying on some continuum. But yeah, I think these conditional sensitivities are really important.
I think that goes back to something Ida was saying, that when we observe or when we look at the ways that machines who play Go or machines that play chess make decisions, they don't make the decisions that a human would make because of their different kinds of affordances, right? And so which gets me back to the question of benchmarks, right? Do we want, like, when we're looking at a machine that passes a given benchmark, if we're not concerned with how it passes the benchmark, merely the appearance of passing the benchmark, that's a different question than saying creating human-like intelligence, right? An intelligence that appears human might not be functionally the same as a human, right? Insofar as it passes particular benchmarks. So how it passes the benchmarks, as you were saying, is grounded in its different kinds of affordances, right?
Yeah, I think that's really fair. I mean, I think most, even among people who study, I guess among people who do like this neuro-inspired AI approach, I think there's some people who argue like we want human-like intelligence. We think that will play nicely with humans. There's like sociological reasons we think that would be optimal. But then I think the other is just like it's a hedge. It's like a bet on convenience. Like we have this example of something that seems to do a bunch of stuff pretty well, and let's stick to it because that gives us. It's maybe like a regularizer almost. Like it's a bias term. It's like when in doubt, maybe stick to the more human-like intelligence strategy because we know humans can do things. We know we think humans are pretty smart. We don't know what else this algorithm will interact with downstream, but this is at least kind of a nice sanity check. I think you can kind of, I've drawn this analogy of like MapQuest before, like you had like a GPS in your phone that would tell you where to go at each instant. You'd like print out directions ahead of time, and as soon as you stray from those directions, you're pretty lost. So I think there's kind of this idea that like maybe we should stick to human-like intelligence, because at least it's a reference frame as we're getting to something that is more and more intelligent, that like if we've made it a little bit human-like, we can build in the direction of other ways that our humans are intelligent too.
And also just to that point, our thinking is, I think when Darwin sort of commented on specialization and a niche construction and species, that one of the things that was said about sort of hominids is that they began to spread across all sorts of environments, right? So they went from the narrow AI of animals specialized in their niches to the general AI of being able to live from the North Pole through the equator to the South Pole, right? So in other words, I think one of the interesting things about this, the point I was trying to make about structure, is that it seemed as though primates, hominids, discovered exploitable structure in the world that wouldn't be obvious. A snake living in the desert isn't going to go, actually, it's possible to live in the ocean as well, right? In other words, I think all I was trying to say is that the more intelligent, a thing is, the more general it can be in its exploitation of structure in the world. And that's what's so fascinating. And humans, to your point, seem to be able to exploit, for good or bad, unfortunately, almost anything, right?
Yeah.
So it's the generalizability of exploitation that is, I think, one of the reasons why humans are interesting, because it seems like they're finding some general structure discovering algorithm. Right?
Yeah, I think that's why I think humans are so often like the reference for machines. Like every animal is equally evolved in some sense. They've all like evolved very specifically for their niches. If we're interested, we kind of think of intelligence as this thing that humans seem to be uniquely good at, this transferability. Although I watched a documentary, back to dolphins. I watched a documentary on dolphins early in the pandemic, and they also are amazingly good at adapting to different environments. Like you can look at bottlenose dolphin populations in different parts of the world, and they have like completely different hunting strategies. There's these dolphins that swim up on the beach, grab fish, and then come back, and like all the teeth are graded down on one side of their mouth.
Well, Kim, I'm going to send you our dolphins, right? I didn't know you were so into dolphins, so you have to meet our simulated dolphin immediately. Okay.
Wait.
All right.
I mean, to that point, octopi are good at that too. I mean, we've got lots of stories about octopi in captivity that squirt water at lights and so on and so forth, right? I too am team octopus. But insofar as John is talking about, exploiting things in the environment, essentially he's talking about what Dewey says is one of the unique things that humans do super well. It's converting, the relationship of means and ends for the sake of determined action across a broad variety of situations, given how we are embodied. And every organism can do that for the sake of its own, say, maintenance of equilibrium with the environment. But humans have such a broad capacity to adapt the environment to suit us, or to adapt to the environment within our given capacities, that it appears to outstrip other animals.
But that quality is very necessary for human survival as well. Like they would not survive otherwise.
Yeah, exactly.
So how does that make it a different, adaptable, evolved sort of quality than what a dolphin can do when it wants to eat on the beach or underwater?
Well, so one, a dolphin would need particular attributes to move around on a beach that it does not possess.
I mean, she said it does that. I mean, it's basically a question of intensity of the thing, I guess. You're saying whatever intelligence is that allows you to explore and adapt is a thing, but humans may have it at more intensity because it needed it to survive. And it becomes an evolution thing, not a unique thing to humans. It's just
yes and no. I wouldn't say it's just a matter of intensity. It's a matter of the ways that we the ways that we do it, and the broad kinds of things, which is grounded in our biophysical organization, right? So I don't have claws, right? So I need a knife. My cat has claws, and so she can do different things. So there's no functional need for her to engage in a process of inquiry to develop a knife. I don't have fur, so I have to engage in different processes of inquiry to regulate my temperature. I'm not, well armored. I'm, kind of squishy and things like that, right? So You don't
seem very squishy to me, Jonathan.
Well, philosophy causes you to develop a thick skin, so.
Also, I mean, so I think there's a field of robotics that's maybe really closely related to like some of the interesting things you're talking about, like soft-bodied robotics. And they talk about this idea a lot, that a lot of our intelligence is due to the material properties of our body. Like, I think one thing people always talk about how octopi can like unscrew jar lids. And I think, like, you know, they're very smart, they're really good at stuff, but like that's actually like not as distant in the action space that octopuses have available to them, like, you know, sectioning onto stuff and squirming their arms around, than it might be for, you know, a dolphin, which probably has nothing that can grab onto anything. Yeah, I mean, the like with the dolphins that are hunting on beaches, they're pretty limited in their ability to navigate the beach. They have to they basically like shoal the fish in and then ride a wave up, grab the fish, and get sucked back into the ocean. And if they mistime it, they're in a lot of trouble. So, you know, I mean, humans have very general purpose bodies, arguably. Like, that's the whole opposable thumb argument, is that like that lets us use tools, that gives us a lot of that basically redefines what your body is. Your body is whatever you're holding.
Well, Kim, I think it's like getting to sort of midnight hour. I mean, you don't seem remotely tired, and you still seem to be sharp.
I'm having fun.
To be sharp than everyone else.
Questions.
YouTube replay, and they go, "How did it get to dolphins eating on a beach?"
I hope so. But yeah. I mean, we could definitely sign off soon. I didn't have a good way to segue back to this, but I did want to say, I think Montreal asked, you know, how you can, if like basically this idea about like if the behavior is overlapping with the neural network in the brain, is like the cognitive operation overlapping? And we all kind of had a version of no. And then I think you mentioned also that you're interested in thinking about how to use these to study the brain. And if the answer is no, that maybe it seems like a simple answer of like, well, they're not necessarily relevant. And I think one approach that people have used is basically like model comparison. You have different neural architectures that are aligned on their behavior, but have some different constraints associated with them. And you can say it's more like A than B. It doesn't necessarily mean B is doing it, but you can like interpolate and compare in this space. So you can like use activity in neural networks as regressors as one way of testing a hypothesis, I think that's like the Yeomans and DeCarlo style of doing it. But yeah, I think definitely the idea is like you don't want to assume either one is exactly like what the brain is doing, but you can use that as like a space of like a computation dragged out over a distance in the neural network and used as a reference for interpolation.
Yeah, thanks for that.
I just want to say that was okay. I just want to say that we promised a couple of people will read their questions, but I can just send it to you, or do you want me to read them quickly?
How many questions?
I think there's just like no. I just read two. I'm just gonna read them just so that like, you know, it's in the space. Ella, who asked us to ask her question, asks, given that human brain has a very developed cortex, including PFC, is it possible that the role of hippocampus in human is very different from its role in mice and rodents? When drawing the parallel across different species is valid. So that's one question. And another one is basically, I will send you the rest of the questions.
Okay. Because yeah, I mean, that one actually I think has a pretty short answer, like definitely yes. Yeah.
All right. So Kim, you have been our champion. I feel like we need to send you like a champion, maybe a champion dolphin or something, to like maybe like a stuffed dolphin.
Perhaps, you know, when we did our study with the dolphin in an assisted living facility, they gave each other a stuffed dolphin trophy. So I think I may have to break into that assisted living facility and steal it for you, Kim.
At least send me a picture.
I will. I absolutely will.
Yeah. I do love dolphins.
John, I have dolphins here. You can just borrow one.
Yeah, so that is going to be, we're going to seriously follow up on that.
Thanks. This was delightful. This was everything I hoped it would be. I was really craving this kind of like scientific, social, hybrid interaction. So I'm very grateful for you guys for inviting me.
Well, you should come back and then interact.
I'm afraid we're going to have to have you back. Yes.
Yeah.
Absolutely.
Thank you so much, honestly.
Thank you,
you, Jonathan and Montreal, for being
Thank
here.
you everyone who asked questions.
We got all zoological. All right.
Thank you, dolphins.
Bye. Thanks, everybody.
Yes.
Bye.
Thank you, everyone.
Good night.